Hello there, and welcome. Tonight I want to take you somewhere extraordinary, somewhere that exists not in the physical realm of stars and planets that we can see through telescopes, but in the quiet spaces of imagination where the impossible becomes not just possible, but beautifully, peacefully intriguing. As you settle into wherever you are right now, perhaps in your bed with the covers pulled up just right, or maybe on a couch with the soft glow of a screen providing the only light in your room, I want you to know that we're about to embark on a journey together, you and I, through one of the most wonderfully strange questions that has ever drifted through my mind in those quiet moments before sleep. Before we begin this journey together, I'm curious about where you're joining me from tonight. What corner of our planet are you in, and what time is it there as these words reach you? Perhaps it's late at night where you are, and the world outside your window has grown quiet and still, or maybe you're listening during a peaceful afternoon, seeking a moment of calm in your day. Wherever and whenever you are, if this journey resonates with you, if you find yourself drawn into this cosmic contemplation, consider leaving a gentle like or subscribing so we can continue exploring these peaceful mysteries together on other nights, other journeys into the vast unknown that surrounds us all. These small connections we make across the darkness, across distances, they matter more than you might think, creating a web of wonder that spans our entire world. The question I want to explore with you tonight is one that might seem, at first, completely absurd, entirely impossible, maybe even a little bit silly. And yet, as we'll discover together over the next few hours, it's a question that opens doorways into understanding not just the universe around us, but our place within it, our connection to scales both impossibly small and incomprehensibly vast. The question is this: what if atoms could be bigger than planets? I know, even saying it out loud feels like breaking some fundamental rule of reality, doesn't it? Atoms are supposed to be tiny, so small we can't see them, so minuscule that millions of them could dance on the head of a pin, while planets are enormous, massive spheres that hold cities and oceans and entire civilizations. How could we even imagine reversing that relationship? But here's what I find fascinating about this question, and why I think it's perfect for our contemplation tonight. Sometimes the most profound insights come not from studying what is, but from gently, carefully imagining what could be, what might exist in some other corner of reality, or what could help us understand our own reality better by seeing it from an entirely different perspective. When we ask what if atoms could be bigger than planets, we're not really trying to rewrite the laws of physics, though we'll play with them a bit. Instead, we're using this impossible idea as a lens, a special way of seeing that might reveal things about atoms, about planets, about size and scale, and the nature of existence itself that we might never notice if we only looked at things the way they actually are. You see, there's something almost magical that happens when we allow ourselves to consider the impossible. Our minds, usually so focused on the practical, the real, the immediate concerns of daily life, suddenly have permission to wander, to explore, to make connections they wouldn't ordinarily make. And in that wandering, in that gentle exploration, we often find not just entertainment or distraction, but genuine insight, genuine wonder, genuine peace. Tonight, as we explore this question together, I invite you to let your mind wander with mine, to let go of the need for everything to make perfect sense, to be perfectly possible, and instead to float with me in this space of what if, of maybe, of perhaps. The universe we live in is already so strange, so full of mysteries and paradoxes and things that shouldn't be possible but somehow are, that adding one more impossibility to the mix hardly seems unreasonable. After all, we live in a cosmos where time can slow down and speed up depending on how fast you're moving or how close you are to a massive object. We live in a reality where particles can be in two places at once, where empty space isn't really empty but seethes with virtual particles popping in and out of existence, where the act of observing something can change what it is. Compared to these actual, verified, scientifically proven strangenesses, the idea of a planet-sized atom almost seems quaint, doesn't it? As we begin this exploration, I want you to understand that we're not going to rush through this idea. We're going to take our time, let each concept settle like dust in still air, let each image form slowly in your mind like a photograph developing in a dark room. There's no hurry here, no deadline to meet, no test at the end. This is purely for the joy of wondering, for the peace that comes from contemplating something vast and strange and beautiful. We're going to move through this question layer by layer, starting with what we know about atoms and planets as they actually are, then gently, carefully, beginning to imagine how things might be different, what it would mean, what it would look like, what it would feel like if atoms could indeed be bigger than planets. I find there's something deeply calming about thinking about scales that are either much smaller or much larger than our everyday human scale. When we think about atoms, those tiny building blocks that make up everything we see and touch and are, we're entering a realm where our usual concerns and worries simply don't apply. The problems that might be keeping you awake tonight, the stresses of your day, they don't exist at the atomic scale. Down there, in that tiny realm, there are only probability clouds and energy levels and the endless dance of electrons around nuclei. Similarly, when we think about planetary scales, about vast spheres of rock and gas and ice spinning slowly through the darkness of space, our human troubles again fade into insignificance. From the perspective of a planet, our entire lives are less than a blink, our biggest achievements and failures equally invisible. But tonight, we're going to do something even more interesting. We're going to blend these scales to imagine them overlapping and interchanging in ways that nature, as far as we know, never intended. We're going to let atoms swell like balloons until they dwarf mountains, until they rival moons, until they surpass even the great gas giants of our solar system. And we're going to imagine planets shrinking, condensing, becoming dense and small and quantum, behaving according to the strange rules that govern the microscopic world rather than the familiar physics of our everyday experience. This might sound like pure fantasy, and in many ways it is. But here's the beautiful thing about human imagination. Even our fantasies are grounded in some kind of reality. When we imagine a planet-sized atom, we're not just making things up randomly. We're taking what we know about atoms, their structure, their behavior, their fundamental properties, and we're extrapolating, extending, exploring what would happen if we could somehow change their scale while keeping their essential nature intact. And in doing this, we might actually learn something real about atoms, about planets, about the universe itself. Scientists do this kind of thing all the time, though they usually call it something more formal, like thought experiments or theoretical modelling. Einstein imagined riding on a beam of light and revolutionized our understanding of space and time. Schrödinger imagined a cat that was simultaneously alive and dead and helped us understand the paradoxes of quantum mechanics. Tonight, we're joining that tradition, though our goal is not to revolutionize physics, but simply to wonder, to explore, to find peace and fascination in the consideration of something beautifully impossible. As we continue, you might find your mind resisting some of these ideas. That's perfectly natural. Our brains are wired to understand the world at a certain scale, the scale at which we live our daily lives. We intuitively understand things that are about our size, that move at about our speed, that exist for about our time scale. Atoms and planets both exist outside these comfortable boundaries, and when we start mixing them together, our intuition can get a bit confused. But I encourage you to lean into that confusion, to find it not frustrating but freeing. When our usual ways of understanding break down, we're forced to think in new ways, to see in new ways, and sometimes to dream in new ways. The journey we're taking tonight will have many stages, many layers of exploration. We'll begin by really understanding what atoms and planets are, how they're similar and how they're different, what makes each of them unique and special in the grand hierarchy of cosmic structures. Then we'll start to play with these concepts, to stretch and squeeze them like cosmic clay, seeing what shapes emerge. We'll explore what scientists have actually discovered about exotic states of matter that blur the lines between the microscopic and the macroscopic, between the quantum and the classical. We'll imagine what it would be like to live in a universe where atoms could be bigger than planets, what the rules of such a universe might be, what kinds of structures and phenomena might exist there. Throughout all of this, I want you to remember that this is a journey we're taking together. Even though I'm the one speaking these words and you're the one listening to them, we're companions in this exploration. Your imagination is just as important as mine in bringing these ideas to life. When I describe a planet-sized atom, the image that forms in your mind is unique to you, influenced by your own experiences, your own understanding, your own dreams. The giant atom you imagine might be different from the one I imagine, and that's not just okay, it's wonderful. It means that together, we're creating not just one impossible universe, but potentially millions of them, each slightly different, each uniquely beautiful. There's also something I want to share with you about why I find this particular question so fascinating, why out of all the impossible things we could imagine, this one calls to me. You see, atoms and planets represent two extremes of existence, two boundaries of the physical world as we know it. Atoms are about as small as things can get while still being things in the conventional sense. Below atoms, we get into subatomic particles, and below those, we get into the realm of pure energy and quantum fields, where the very concept of thing starts to break down. Planets, on the other hand, are among the largest single objects in the universe. Yes, stars are bigger, and galaxies are much bigger, but planets occupy a special place as the largest solid objects, the largest things that you could, in principle, stand on, walk around, explore. So when we imagine atoms being bigger than planets, we're not just playing with size, we're inverting the entire hierarchy of nature, turning the smallest things into the largest things, and implying that the largest things might become the smallest. It's a complete reversal of the cosmic order, and there's something both unsettling and thrilling about that. It makes us question our assumptions about what's fundamental and what's derived, what's basic and what's complex, what's important and what's trivial. But perhaps most importantly for our purposes tonight, thinking about planet-sized atoms is an exercise in peaceful impossibility. Unlike many of the impossible things we might imagine, like faster-than-light travel or time machines or parallel universes, planet-sized atoms don't come with any baggage of danger or paradox or existential threat. They're purely wondrous, purely strange, purely fascinating. They don't threaten our existence or challenge our morality, or force us to confront difficult questions about the nature of consciousness or free will. They simply are, or rather, they simply aren't, but could be imagined to be, and in that imagination, we find a kind of pure, peaceful contemplation. As you listen to my voice tonight, I want you to let yourself sink into this contemplation. Don't worry about remembering every detail or following every argument. This isn't a lecture or a lesson. It's more like a lullaby if lullabies were about cosmic impossibilities instead of twinkling stars and sleeping babies. Let the ideas wash over you like gentle waves, each one carrying you a little further from the shore of everyday reality and out into the vast ocean of possibility. Some ideas will resonate with you more than others, and that's perfectly fine. Take what speaks to you, and let the rest drift by like clouds across a night sky. I should mention that throughout our journey tonight, we'll encounter real science alongside our speculation. We'll talk about actual discoveries that scientists have made about atoms and planets, real phenomena that exist in our universe that might be related to our imaginary planet-sized atoms. But we'll always be clear about what's real and what's imagined, what's been observed, and what's being speculated. The line between science and science fiction can be thin sometimes, especially when we're dealing with the extremes of scale and possibility, but it's an important line to maintain. The real universe is strange enough without us needing to make things up, but sometimes making things up helps us appreciate just how strange the real universe actually is. You might wonder why we should bother thinking about impossible things at all. If atoms can't really be bigger than planets, if this whole idea is just a fantasy, what's the point? Well, I believe there are several points, several reasons why this kind of imaginative exploration is not just entertaining but actually valuable, maybe even important. First, it exercises our capacity for wonder, that fundamental human ability to be amazed and delighted by ideas, by possibilities, by the sheer strangeness and beauty of existence. In our daily lives, it's easy for wonder to get buried under routine and responsibility, but it's still there, waiting to be awakened, and thinking about impossible things is one of the best ways to wake it up. Second, imagining impossible things helps us better understand possible things. By pushing concepts to their breaking point, by exploring what would happen if the rules were different, we gain a deeper appreciation for why the rules are what they are. When we imagine atoms being bigger than planets, we have to think about what makes atoms atoms and what makes planets planets. What would be preserved and what would be lost if we changed their scales? And in doing that thinking, we come to better understand both atoms and planets as they actually are. Third, and perhaps most relevant for tonight, thinking about peaceful impossibilities is a form of meditation, a way of calming the mind and finding tranquility in pure thought. When we're imagining planet-sized atoms, we're not worrying about tomorrow's meetings or yesterday's mistakes. We're not anxious about the future or regretful about the past. We're simply present in the moment of imagination, exploring ideas that have no practical consequence but infinite theoretical interest. It's a form of mental play, and play, as children know but adults often forget, is one of the most restorative things we can do. As we move forward in our exploration, I want to paint a picture for you of the kind of universe we're imagining. Picture, if you will, a vast darkness punctuated not by stars and planets as we know them, but by enormous shimmering atoms, each one the size of Jupiter or Saturn, their electron clouds visible as aurora-like glows surrounding dense, bright nuclei. These giant atoms drift through space, occasionally coming close enough to share electrons, forming molecular bonds that span light years. The chemistry of this universe operates on a timescale of millions of years, with reactions that would take nanoseconds in our world playing out like slow-motion ballets across cosmic time. In this universe, what we call planets are tiny subatomic particles, too small to see, too small to matter except in vast aggregations. Entire civilizations, if they could exist at such scales, would be less than quantum fluctuations in the electron clouds of these giant atoms. The history of a species from birth to extinction would be less than a vibration, less than a tremor in the vast, slow dance of atomic forces scaled up to cosmic size. But we're getting ahead of ourselves. Before we can fully appreciate this inverted universe, we need to understand the components we're working with. We need to truly grasp what atoms are, not just as abstract concepts from chemistry class, but as real, physical entities with structure and behavior and properties that make them what they are. And we need to understand planets in the same way, not just as big rocks in space, but as complex systems with their own internal dynamics, their own histories, their own futures. So let's begin that journey of understanding. Let's start with the familiar and work our way toward the fantastic. Let's take what we know and stretch it, carefully and thoughtfully, into what we can imagine. And through it all, let's maintain that sense of peaceful wonder, that calm curiosity that makes exploration not a struggle but a joy. You know, there's something beautiful about the fact that we can even ask this question, that our minds are capable of conceiving of something as wonderfully absurd as planet-sized atoms. No other species on Earth, as far as we know, can do this kind of abstract imagination. A dog can imagine a bone that's not there, maybe, or a cat can dream of catching a mouse. But only humans can imagine atoms the size of planets, can take two completely separate concepts from totally different scales of reality and smash them together in our minds just to see what happens. This capacity for abstract imagination might be our greatest gift as a species, is what allows us to do science, to do art, to tell stories, to dream of better futures and learn from imagined pasts. And tonight, we're using this gift not for any practical purpose, not to solve any problem or create any product, but simply for the pure joy of imagination itself. We're imagining because we can, because it's peaceful, because it's wonderful, and because sometimes the best thing to do before sleep is to fill our minds with impossible wonders rather than possible worries. As we continue, you might notice that your breathing has already begun to slow, that your muscles have started to relax. This is natural and good. The contemplation of cosmic scales, whether impossibly large or impossibly small, has a way of putting our bodies at ease even as it engages our minds. There's no danger here, no urgency, no need for the fight or flight responses that evolution has equipped us with. We're safe in our imagination, free to explore without risk, to wonder without consequence. The question of planet-sized atoms also touches on something fundamental about how we understand reality. We tend to think of size as absolute, as fixed. A hydrogen atom is about 1 meters across, and Earth is about 12,242,000 meters across, and that's that. But what if size is more relative than we think? What if the universe could be stretched or compressed in ways that would make atoms and planets trade places? This isn't just wild speculation. In some interpretations of cosmology and quantum mechanics, size and scale are more fluid than our everyday experience suggests. Consider for a moment the concept of scale invariance. The idea that the laws of physics might look the same at different scales if you adjust all the relevant parameters appropriately. It's a concept that shows up in various areas of physics, from critical phenomena to string theory. While it doesn't actually mean that atoms could be planet-sized in our universe, it suggests that the relationship between different scales might be more subtle and interesting than simple multiplication by powers of 10. Or think about the holographic principle, the strange idea from theoretical physics that all the information in a volume of space can be encoded on the boundary of that space, like a hologram. If this is true, and some physicists think it might be, then our usual notions of inside and outside, of big and small, might be more like convenient approximations than fundamental truths. In a holographic universe, the distinction between an atom and a planet might be less absolute than we imagine. But we're getting into deep waters here, and I promised this would be a peaceful journey, not a challenging one. So let's pull back from the edge of theoretical physics and return to our simple, wonderful question. What if atoms could be bigger than planets? Let's approach it not as physicists trying to prove or disprove something, but as dreamers, as imaginers, as peaceful contemplators of the cosmic what-if. One of the things I love about this question is that it makes us think about what we really mean by atom and planet. Is an atom defined by its size or by its structure? Is a planet defined by its mass or by its behavior? If we had an object with the structure of an atom but the size of a planet, would it be a giant atom or something else entirely? If we had an object with the mass of a planet but the size of an atom, would it be a tiny planet or, again, something completely different? These might seem like semantic questions, but they point to something deeper about how we categorize and understand the world. We like to put things in neat boxes to say this is an atom and that is a planet, but nature doesn't always respect our categories. There are objects in the universe that blur the lines between different classifications, that exist in the grey areas between our neat definitions. For example, consider brown dwarfs, those objects that are too big to be planets but too small to be stars. They don't fit neatly into either category, and astronomers have had lengthy debates about how to classify them. Or consider the exotic objects called quark stars, hypothetical objects that would be made of quark matter, something denser than the matter in atomic nuclei. These would be stellar mass objects with properties unlike anything we normally encounter, neither truly stars nor planets, nor giant atoms, but something unique. As we prepare to dive deeper into our exploration, to really examine what atoms and planets are and what they could be, I want you to carry with you this sense of flexibility, this willingness to let categories blur and definitions shift. The universe is under no obligation to fit into the mental boxes we create for it, and some of the most interesting discoveries come from recognizing when something doesn't fit, when we need to create new categories or abandon old ones. The night is still young, or perhaps it's very late where you are, but either way, we have time. We have all the time we need to explore this question properly, to turn it over in our minds like a jewel, examining each facet, watching how the light plays differently across each surface. There's no rush, no hurry. The planet-sized atoms of our imagination will wait for us, patient and eternal, as we slowly work our way toward understanding what they might be and what they might mean. Let's begin with something familiar, something you can hold in your mind as easily as you might hold a small stone in your hand. Picture, if you will, a grain of sand. Perhaps you've held one recently, at a beach or in a garden, or perhaps you're imagining one from memory, tiny and gritty between your fingers. This grain of sand, so small you might lose it with a casual brush of your hand, contains approximately 50 quintillion atoms. That's 50,000 atoms, a number so large that if you tried to count them, one per second, it would take you about 1.6 trillion years, more than 100 times the age of the universe. And yet, from the perspective of an atom, that grain of sand is an entire universe, vast and complex beyond imagination. If an atom were the size of a marble, that grain of sand would be about 200 meters across, like a huge stadium filled with marbles. But atoms aren't the size of marbles. They're so small that we need to completely recalibrate our sense of scale to even begin to understand them. An atom is to a grain of sand as a grain of sand is to the Earth. Sit with that for a moment. The same ratio that separates a tiny grain of sand from our entire planet separates an atom from that grain of sand. We live our lives in the middle of an enormous range of scales, and we're remarkably bad at intuitively understanding anything too far from our familiar human scale. We can understand things that are about our size, from perhaps a millimetre to a few kilometres, but beyond that, our intuition starts to fail us. We know intellectually that atoms are small and planets are large, but we don't really feel it, not in the way we feel the weight of a book or the distance to the grocery store. This failure of intuition is actually a gift tonight, because it means we can play with these scales, imagine them differently, without our deep instincts telling us we're doing something wrong. Let's climb the ladder of scales slowly, starting from the very small and working our way up to the very large, pausing at each rung to really appreciate where we are. At the smallest scale we can meaningfully talk about, we have subatomic particles like electrons and quarks. An electron, if it has a size at all, is less than 10 to 18 meters across. So small that we're not even sure it has a size in the conventional sense. It might be a point, a zero-dimensional dot of charge and mass, or it might have some incredibly tiny extent that we haven't been able to measure yet. Moving up from electrons, we come to protons and neutrons, the particles that make up atomic nuclei. These are about 10 to 15 meters across, 1,000 times larger than an electron's maximum possible size, but still incredibly tiny. A proton is to a grain of sand as a grain of sand is to something about 1,000 kilometers across, like the distance from New York to Florida. These nuclear particles are made of quarks held together by the strong force, one of the 4 fundamental forces of nature, and the way quarks combine to form protons and neutrons is one of the most beautiful examples of emergence in physics, where simple components create complex behaviors. Now we come to atoms themselves, those legendary building blocks of matter that philosophers speculated about for millennia, before scientists finally proved their existence. A typical atom is about 10 to 10 meters across, about 100,000 times larger than a proton. But here's where things get interesting and strange. Most of that space is empty. If the nucleus of an atom were the size of a marble in the centre of a football stadium, the electrons would be like gnats buzzing around the outer walls. The atom is mostly nothing, mostly empty space, with just a tiny nucleus and even tinier electrons occupying an insignificant fraction of its volume. This emptiness is one of the most counterintuitive facts about the physical world. The chair you're sitting on, the device you're using to listen to this, your own body, all of these seemingly solid objects are mostly empty space. If you could somehow remove all the empty space from all the atoms in your body, compress everything down so that all the particles were touching, you would be smaller than a grain of sand. All of humanity, all 7 billion of us, compressed in this way, would fit into a sugar cube. The Earth itself, all 6 trillion kilograms of it, would become a sphere only about 300 meters across if you removed all the atomic empty space. But of course, we can't actually remove that empty space, because it's not really empty in the way we usually think of emptiness. It's filled with electromagnetic fields, with the probability clouds of electrons, with virtual particles popping in and out of existence, with all the quantum weirdness that makes atoms atoms. The emptiness of atoms is an active, dynamic emptiness, full of potential and energy and the constant dance of quantum mechanics. Moving up in scale from individual atoms, we come to molecules, collections of atoms bound together by sharing or exchanging electrons. Molecules can be as simple as 2 hydrogen atoms stuck together, or as complex as DNA with its billions of atoms arranged in a precise double helix. The largest molecules we know of, some proteins and synthetic polymers, can be almost visible to the naked eye, bridging the gap between the atomic world and our human-scale world. Then we have the realm of the very small but visible, bacteria, cells, dust particles, the width of a human hair. A typical bacterium is about 10 to 6 meters across, 10,000 times larger than an atom. A human cell is 10 times larger still, and a human hair is about 100 micrometers thick, 1,000,000 times wider than an atom. We're still in the realm of the tiny here, things that require microscopes to see properly, but we're getting closer to our familiar scale. Now, we enter the human scale, the world of everyday objects, a pencil, a coffee, cup, a basketball, a person, a tree, a house. These are the things our brains evolved to understand, the scales at which our intuition works well. We can judge distances and sizes and speeds in this realm without conscious calculation. We know how long it takes to walk across a room, how heavy a book feels, how tall a building looks. This is our home scale, where we spend most of our mental time. But let's keep climbing. From houses to city blocks, from city blocks to cities themselves. A typical city might be 10 to 50 kilometers across, and now we're starting to push the limits of human intuition again. We can see a city from an airplane and get a sense of its size, but it's hard to really feel it the way we feel the size of a room. The Earth itself is about 12,742 kilometers in diameter, and while we can intellectually understand this number, can any of us really grasp it intuitively? Can you truly imagine walking all the way around the equator, taking 50 million steps, one after another after another? Earth is huge from our perspective, but it's tiny compared to Jupiter, the giant of our solar system. Jupiter is about 11 times wider than Earth, which means you could fit over the 300 Earths inside Jupiter's volume. But Jupiter is still a planet, still a single, discrete object orbiting the Sun. The Sun itself dwarfs Jupiter, with a diameter about 10 times larger. You could fit about 1,000 Jupiters inside the Sun, or about 1.3 million Earths. And yet our Sun is just an average star, neither particularly large nor particularly small. There are stars like VI Canis Majoris that are over 1,400 times wider than our Sun. If VI Canis Majoris were placed at the centre of our solar system, its surface would extend beyond the orbit of Jupiter. These hypergiant stars are among the largest single objects in the universe, so large that light itself takes hours to travel from one side to the other. But even these enormous stars are tiny compared to the structures they form. A typical galaxy like our Milky Way is about 100,000 light-years across, containing hundreds of billions of stars along with vast clouds of gas and dust. A light-year, the distance light travels in 1 year, is about 9.5 trillion kilometers, so our galaxy is about 1,000 kilometers across, a number so large it becomes meaningless, just a string of zeros that our brains can't really process. And galaxies themselves cluster together into groups and clusters and superclusters, forming a cosmic web that spans billions of light-years. The observable universe is about 93 billion light-years in diameter, though the actual universe might be much larger or even infinite. At these scales, even galaxies become like atoms, tiny points in a vast structure that we can barely begin to map. Now, having climbed from the smallest to the largest, from electrons to the observable universe, let's pause and consider what we've learned. The range of scales in the universe is almost incomprehensibly vast. An atom is to the Earth as the Earth is to something about 100 times the size of the Sun. The observable universe is to an atom as an atom is to something about 10⁻³ meters across, far smaller than anything we can meaningfully talk about in physics. This vast range of scales isn't just a curiosity, it's fundamental to how the universe works. Different phenomena dominate at different scales. At the quantum scale, uncertainty and probability rule. At the atomic and molecular scale, electromagnetic forces dominate. At the human scale, gravity starts to become noticeable, but is still weak enough that we can jump. At planetary scales, gravity dominates everything, shaping worlds into spheres and governing orbits. At galactic scales, dark matter becomes important, that mysterious substance that we can't see, but that seems to outweigh normal matter by a factor of 5. At the largest scales, dark energy takes over, that even more mysterious force that's causing the universe to expand faster and faster. Each scale has its own music, its own dance, its own rules, and yet, remarkably, they're all connected. The atoms in your body were forged in the hearts of stars that died billions of years ago. The gravity that holds you to Earth is the same gravity that shapes galaxies. The electromagnetic force that holds molecules together is the same force that carries light across the cosmos. There's a unity underlying the diversity of scales, a coherence to the universe that becomes visible when we step back and look at the whole picture. This is the context in which we ask our question, what if atoms could be bigger than planets? We're not just swapping two sizes, we're imagining a fundamental inversion of the cosmic hierarchy. We're suggesting that the smallest things could become the largest, that the building blocks could become bigger than the buildings. It's a thought that challenges our understanding not just of size, but of the relationship between different scales, of the way the universe organizes itself from the bottom up. But maybe that organization isn't as fixed as we think. Maybe size is more fluid, more negotiable than our everyday experience suggests. After all, the universe itself has changed size dramatically over cosmic time. In the first fraction of a second after the Big Bang, during the period called cosmic inflation, the universe expanded by a factor of at least 10^26, possibly much more. Space itself stretched. carrying everything with it, making the universe enormously larger in an incredibly short time. And in black holes, we see the opposite process, where enormous amounts of matter are compressed into incredibly small volumes. The event horizon of a black hole, the point of no return beyond which nothing can escape, can be thought of as a kind of boundary where our usual notions of space and size break down. Inside a black hole, if our theories are correct, matter is compressed to a point of infinite density called a singularity, where the usual rules of physics cease to apply. These extreme cases suggest that size and scale might not be as absolute as we usually think. Under extreme conditions, the very fabric of space-time can stretch or compress, carrying matter along with it. The atoms in the early universe were, in a sense, much larger relative to the universe than atoms today, simply because the universe itself was so much smaller. And near a black hole, the intense gravity warps space so severely that our usual measurements of distance and size become distorted. There's also the fascinating phenomenon of scaling in physics, where certain systems look the same at different scales. This is called scale invariance or self-similarity, and it shows up in surprising places. The coastline of Britain looks jagged and complex whether you're looking at it from a satellite or examining a small section under a magnifying glass. The branching patterns of rivers look similar to the branching patterns of blood vessels, which look similar to the branching patterns of lightning. These patterns repeat across vastly different scales, suggesting that there might be deep principles that transcend any particular size. In quantum mechanics, we encounter another challenge to our usual notions of size. Quantum particles don't have well-defined positions or sizes in the way classical objects do. An electron in an atom doesn't orbit the nucleus like a planet orbits a star. Instead, it exists in a cloud of probability, simultaneously everywhere and nowhere until it's measured. The size of an electron's orbital, the region where it's likely to be found, depends on its energy state. In highly excited states called Rydberg states, an electron can be found very far from the nucleus, making the atom hundreds or thousands of times larger than normal. These Rydberg atoms are the closest thing in nature to our imaginary planet-sized atoms. While they're still microscopic by our standards, they're giants in the atomic world. A Rydberg atom with its electron in a very high energy state can be almost a millimetre across, large enough to see with the naked eye if we could somehow make it visible. These atoms are extremely fragile, easily disrupted by the slightest disturbance, but they exist, proving that atoms can indeed be much larger than we usually imagine. But what prevents atoms from being even larger? Why can't we have atoms the size of basketballs or buildings or planets? The answer lies in the fundamental forces and constants of nature. The size of a normal atom is determined by a balance between the electromagnetic attraction between the nucleus and electrons and the quantum mechanical tendency of electrons to spread out. This balance point is set by fundamental constants, like the charge of an electron, the mass of an electron, and Planck's constant, which governs quantum behavior. If we could somehow change these constants, we could change the size of atoms. If electrons were lighter, atoms would be larger. If the electromagnetic force were weaker, atoms would be larger. If Planck's constant were larger, atoms would be larger. In a universe with different fundamental constants, atoms could indeed be the size of planets, and planets might be compressed into atom-sized points. But changing these constants would change everything else too. Chemistry would be different, stars would burn differently or not at all, and life as we know it would be impossible. This brings us to an interesting philosophical point. When we imagine planet-sized atoms, are we imagining them in our universe with our laws of physics, somehow circumventing the rules, or are we imagining a different universe with different rules where such things would be natural? Both approaches are valid for our thought experiment, and each leads to different insights. If we imagine planet-sized atoms in our universe, we have to think about how they could exist given the laws we know. Perhaps they're not really atoms in the conventional sense, but something that resembles atoms at a much larger scale. Perhaps they're held together not by electromagnetic forces but by gravity, or some exotic force we haven't discovered yet. Perhaps they exist in a region of space where the fundamental constants are different, a bubble of altered physics floating in our normal universe. On the other hand, if we imagine a universe where planet-sized atoms are natural, we're free to redesign physics from the ground up. In this universe, perhaps what we call planets are the elementary particles, and what we call atoms are complex structures made of many planet particles. Perhaps chemistry happens on a timescale of billions of years, with molecular reactions playing out over cosmic time. Perhaps life, if it exists, operates so slowly that the evolution of a species takes longer than the current age of our universe. Both approaches, the rule-breaking and the rule-changing, help us understand our actual universe better. By imagining how things could be different, we appreciate why they are the way they are. By stretching the boundaries of possibility, we see more clearly where those boundaries lie and why they exist. As we continue our journey through scales, it's worth noting that the human position in this vast hierarchy is rather special. We're almost exactly in the middle, at least in terms of logarithmic scale. The smallest things we can meaningfully talk about in physics are about 1035 meters, the Planck length, and the largest thing we can observe is about 1026 meters, the observable universe. We humans, at about 10 meters, 1 meter, are right in the middle of this range on a logarithmic scale. This might be a coincidence, or it might be telling us something deep about the nature of consciousness and observation. Perhaps intelligence can only emerge at this middle scale, where there's enough complexity to support thought, but not so much that everything becomes statistical and average. Perhaps we're in the Goldilocks zone of size, not too big, not too small, but just right for wondering about planet-sized atoms and atom-sized planets. The scale of human experience also determines how we measure and understand everything else. We invented the meter based on our own size, originally defined as 1/10,000,000th of the distance from the equator to the North Pole. We measure time in seconds, originally based on our heartbeat and the rotation of our planet. We measure temperature based on the freezing and boiling points of water at the pressure we experience at sea level. All of our units, all of our measurements, are fundamentally anthropocentric, based on the accident of our particular size and the conditions on our particular planet. This human-centered perspective makes it even more interesting to imagine inversions of scale, like planet-sized atoms. We're not just imagining different sizes, we're challenging our entire framework for understanding the universe. If atoms were the size of planets, would the intelligent beings in that universe, if they existed, measure things in terms of electron orbits instead of meters? Would they think of what we call planets as subatomic particles, too small to matter except in vast aggregations? The question of scale also touches on some of the deepest mysteries in physics. Why is gravity so much weaker than the other fundamental forces? Why is the universe so big and so old? Why are atoms so small compared to the structures they form? These questions might seem simple, but they point to profound puzzles that physicists are still trying to solve. One intriguing idea is that gravity might actually be as strong as the other forces, but most of its strength leaks into extra dimensions that we can't perceive. In this view, what we experience as the weakness of gravity is just the three-dimensional shadow of a much stronger force operating in higher dimensions. If this is true, then at very small scales, smaller than we've been able to probe experimentally, gravity might become as strong as electromagnetism. This could completely change the behavior of matter at those scales, perhaps allowing for stable structures that we can't imagine with our current understanding. Another possibility is that our universe is just one of many in a vast multiverse, each with different fundamental constants, and therefore different typical sizes for atoms and planets. In some of these universes, atoms might indeed be larger than what we call planets. In others, atoms might not exist at all, or might be replaced by completely different structures we can't imagine. Our universe, with its particular set of constants that allow for atoms much smaller than planets, might be special only because it's the one we happen to inhabit. These ideas might seem like wild speculation, and in many ways they are, but they're grounded in real physics, real mathematics, real attempts to understand the universe at its deepest level. The fact that we can even conceive of such possibilities, that we can imagine universes fundamentally different from our own, is a testament to the power of human thought and the flexibility of mathematics as a language for describing reality. As we near the end of this exploration of scale, let's return to that grain of sand we started with, that tiny speck, barely visible, containing its 50 quintillion atoms. Each of those atoms, if expanded to the size of a planet, would be a world unto itself, with its own complex internal structure, its own dynamics, its own story. The electrons would be like moons, orbiting at vast distances, occasionally jumping from one orbit to another in quantum leaps that would release energy like stellar flares. And if atoms could be the size of planets, what would happen to actual planets? Would they shrink down to atomic size, creating a perfect inversion of our cosmic hierarchy? Would there be planet atoms and atom planets existing side by side, two different organizations of matter at radically different scales? Or would the very concepts of atom and planet lose their meaning, replaced by something else, something we don't have words for yet? Now let us drift inward, leaving behind the vast scales of planets and stars, and enter the atom itself. But we won't rush this journey. We'll descend slowly, like a diver sinking through layers of increasingly mysterious water, until we reach that strange quantum realm where the rules of everyday experience no longer apply. Here, in the heart of matter itself, we'll find not the solid, dependable building blocks we might expect, but something far more beautiful and strange, a shimmering cloud of possibility, a dance of probability and potential that somehow gives rise to everything solid and real in our world. When most of us picture an atom, we probably imagine something like a miniature solar system, a dense nucleus at the center with electrons orbiting around it in neat circular paths. This image, called the Bohr model after the physicist Niels Bohr who proposed it in 1913, is so iconic that it's become the universal symbol for atoms, appearing on everything from science textbooks to nuclear warning signs. But this picture, as useful as it's been for helping us think about atoms, is fundamentally wrong, or at least fundamentally incomplete. The real atom is far stranger, far more interesting, and far more relevant to our question about planet-sized atoms. Let's start with what we know for certain. Every atom has a nucleus, a tiny, dense core containing protons and neutrons. The number of protons determines what element the atom is. 1 proton makes hydrogen, 2 make helium, 6 make carbon, and so on up through the periodic table. Neutrons add mass without changing the element, creating different isotopes. Around this nucleus, in some sense, are electrons, exactly as many electrons as there are protons in a neutral atom, their negative charges balancing the positive charges of the protons. But here's where things get strange. The electrons aren't really orbiting the nucleus, not in the way planets orbit the Sun or satellites orbit Earth. Instead, they exist in what physicists call orbitals, three-dimensional regions of space where an electron is likely to be found. These orbitals aren't paths or trajectories, they're probability clouds, zones of likelihood that tell us where we might find an electron if we look for it, but not where the electron is when we're not looking. This might sound like philosophical hair-splitting, but it's not. It's a fundamental feature of quantum mechanics, the theory that governs the atomic world. According to quantum mechanics, particles like electrons don't have definite positions and velocities at the same time. They exist in what's called a superposition of states, simultaneously being in many places at once until they're observed or measured, at which point they collapse into a definite state. This isn't just a limitation of our measurement tools, it seems to be a basic fact about how reality works at the quantum scale. Imagine, if you will, that you're shrinking down, smaller and smaller, approaching an atom of hydrogen, the simplest atom there is. As you get closer, the atom doesn't look like anything at first. There's no visible boundary, no edge where the atom stops and empty space begins. If you could see the electron, which you couldn't, because seeing requires light, and light would disturb the electron, it wouldn't look like a tiny ball zipping around the nucleus. Instead, you'd see something like a fog or a cloud, denser in some places and more diffuse in others. This cloud represents the probability of finding the electron at any given point. In the lowest energy state of hydrogen, called the ground state, this cloud is spherical, denser near the nucleus and fading away gradually as you move outward. There's no sharp edge. The probability just gets smaller and smaller, never quite reaching zero. In principle, there's a tiny, tiny chance of finding the hydrogen atom's electron on the other side of the universe, though the probability is so small that it might as well be zero for all practical purposes. The shape of these probability clouds, these orbitals, is determined by the mathematics of quantum mechanics, specifically by something called the Schrödinger equation. This equation, one of the foundational equations of modern physics, describes how quantum systems evolve over time. When applied to electrons in atoms, it produces a set of allowed orbitals, each with its own shape, size, and energy. These orbitals have names that might sound familiar if you've studied chemistry: s orbitals, spherical; p orbitals, dumbbell-shaped; d orbitals, more complex shapes; and f orbitals, even more complex. What's remarkable about these orbitals is that they're not arbitrary. They're not just one possible way. Electrons could arrange themselves around a nucleus. They're the only ways allowed by the laws of quantum mechanics. An electron in an atom must be in one of these orbitals. It can't be in between. This is why atoms can only absorb and emit light of specific colors. When an electron jumps from one orbital to another, it must absorb or emit exactly the amount of energy corresponding to the difference between those orbitals. This quantization of electron states is what gives atoms their stability. In classical physics, an orbiting electron should continuously emit radiation, losing energy and spiraling into the nucleus in a fraction of a second. But quantum mechanics says the electron can't spiral inward continuously. It can only jump between discrete orbitals. And if it's already in the lowest energy orbital, the ground state, it has nowhere lower to go. It's stuck there, stable, potentially forever. Now, let's think about what this means for our planet-sized atoms. If we simply scaled up a hydrogen atom so that it was the size of Earth, what would we see? The nucleus, normally about 10-15 meters across, would be about 1.3 meters across, about the size of a large beach ball. But this beach ball would weigh about 2 pounds 17 kilograms, about the mass of a modest asteroid, compressed into that small volume. The density would be stupendous, similar to the density of an atomic nucleus, which is about 100 trillion times denser than water. The electron's probability cloud would extend throughout the entire volume of our Earth-sized atom, but it wouldn't be uniform. Near the nucleus, the probability would be highest, though still incredibly diffuse compared to our everyday experience. As you moved outward, the probability would decrease exponentially. At the surface of our Earth-sized atom, about 6,400 kilometers from the nucleus, the probability of finding the electron would be very small, but not zero. If you could somehow see this probability cloud, it might look like a vast spherical fog, denser near the center and fading to invisibility at the edges. But it wouldn't be static. Quantum mechanics tells us that even in its ground state, the electron isn't still. It has what's called zero-point energy, a minimum amount of energy that it can never lose. This means our planet-sized electron cloud would be shimmering, fluctuating, never quite still, like the surface of a lake on a perfectly calm day that still shows tiny ripples from the movement of molecules. But a hydrogen atom is simple, almost boring in its simplicity. What about more complex atoms? As we add more protons to the nucleus and more electrons to the cloud, the situation becomes far more intricate. The electrons don't all crowd into the same orbital. Instead, they fill up orbitals according to specific rules, building up a complex structure of electron shells and subshells. The first electron goes into the lowest energy orbital, the 1s orbital. The second electron can join it there, with opposite spin, a quantum property we haven't discussed yet. But the third electron can't fit. The 1s orbital is full, so it goes into the next available orbital, the 2s orbital, which is larger and higher in energy. As we keep adding electrons, they fill up orbitals in a specific order, creating the structure that gives each element its unique chemical properties. In a planet-sized carbon atom, with its 6 electrons, we'd have 2 electrons in the inner 1s orbital, 2 in the 2s orbital, and 2 in 2p orbitals. Each of these orbitals would be a vast cloud of probability, interpenetrating but distinct, creating a complex 3-dimensional pattern of electron density. The 2p orbitals wouldn't be spherical but would have a dumbbell shape, oriented along different axes. The entire atom would be like a vast multi-layered fog, with different regions of density and different shapes all superimposed on each other. And remember, these electrons aren't just sitting in their orbitals like cars in parking spaces. They're quantum objects, existing in superposition, constantly fluctuating, their properties uncertain until measured. In our planet-sized atom, these fluctuations would be happening on an enormous scale. An electron might be mostly on one side of the atom at one moment, and mostly on the other side a moment later, not because it travelled from one side to the other, but because its probability distribution shifted. This brings us to one of the most mysterious aspects of atoms: quantum entanglement. The electrons in an atom aren't independent, they're entangled with each other, their quantum states linked in ways that classical physics can't explain. When one electron is in a particular state, it affects what states the other electrons can be in. This isn't because they're pushing on each other or communicating in any classical sense. It's a purely quantum phenomenon, a correlation that exists outside of space and time as we usually understand them. In our planet-sized atom, this entanglement would mean that the vast electron clouds aren't just overlapping, but are fundamentally connected. A measurement on one side of the atom could instantaneously affect the probability distribution on the other side, not through any signal travelling between them, but through the mysterious non-local connections of quantum mechanics. The entire atom would be a single quantum system, coherent and unified despite its enormous size. But atoms aren't isolated systems. They interact with their environment, with light, with other atoms. These interactions are what make chemistry possible, what allow atoms to form molecules and molecules to form the complex structures of life. In our normal-sized world, these interactions happen incredibly quickly. Electrons jump between orbitals in femtoseconds, 10^15 seconds. Molecules vibrate billions of times per second. Chemical reactions occur in fractions of a second. What would these interactions look like in planet-sized atoms? If we simply scaled up the size without changing anything else, the interactions would slow down dramatically. Light would take minutes to cross from one side of the atom to the other. An electron jumping from one orbital to another would be like a vast cloud of probability slowly reshaping itself over hours or days. Chemical reactions between planet-sized atoms would take millions of years to complete. But perhaps in a universe with planet-sized atoms, other things would scale differently. Perhaps light would travel faster, or time itself would run differently. Or perhaps the slow pace would be the natural rhythm of that universe, with any intelligent beings adapted to think and live on those vast timescales. A conversation between such beings might take centuries, a lifetime might span billions of years, and the entire history of a civilization might play out over timescales that dwarf the current age of our universe. There's another aspect of atoms we need to consider, their interaction with light. Atoms can absorb and emit photons, particles of light, when electrons jump between orbitals. Each element has its own unique spectrum, specific colours of light that it can absorb or emit like a cosmic fingerprint. This is how we know what distant stars are made of. We look at the light they emit and see the spectral lines of different elements. In a planet-sized atom, these interactions with light would be dramatic. When an electron jumped from a high-energy orbital to a lower one, it wouldn't emit a single photon but a burst of light that might be visible from millions of kilometers away. The atom would glow and flicker as electrons jumped between orbitals, creating a light show that would put any aurora to shame. Different elements would glow in different colors. Planet-sized hydrogen would emit red and blue-green light. Planet-sized sodium would glow yellow. Planet-sized mercury would emit blue and green. The absorption of light would be equally dramatic. If the right color of light passed through a planet-sized atom, it might be completely absorbed, the energy causing an electron to jump to a higher orbital. The atom would suddenly dim in that color, creating a shadow that could be seen from space. These planet-sized atoms would be like cosmic filters, selectively absorbing and emitting specific colors of light, painting the universe in their spectral hues. But we've been assuming that planet-sized atoms would follow the same quantum mechanical rules as normal atoms, just scaled up. What if the scaling itself changed the rules? What if at that size quantum effects began to break down, replaced by something else, something we haven't discovered yet? There's actually some precedent for this idea. Quantum mechanics works perfectly for small systems, but as systems get larger, quantum effects tend to average out, replaced by classical behavior. This is called decoherence, and it's why we don't see quantum superposition. In our everyday lives, a baseball doesn't exist in multiple places at once. It has a definite position and velocity. A cat is either alive or dead, not both at the same time, despite Schrödinger's famous thought experiment. The boundary between quantum and classical behavior isn't sharp, and physicists are still trying to understand exactly how and why quantum mechanics gives way to classical mechanics at larger scales. Some theories suggest that gravity, negligible at the atomic scale, becomes important at larger scales and causes decoherence. Others propose that the interaction with the environment causes quantum states to collapse into classical ones. If planet-sized atoms existed, They would be right at this boundary between quantum and classical. Would their electrons still exist in probability clouds, or would they have definite positions? Would they still jump between discrete orbitals, or would they spiral continuously? Would quantum entanglement still hold across planetary distances, or would it break down? These questions touch on some of the deepest mysteries in physics: the relationship between quantum mechanics and gravity, the nature of measurement and observation, the emergence of classical from quantum behavior. These are all active areas of research, puzzles that the greatest minds in physics are still trying to solve. Our thought experiment about planet-sized atoms leads us right to the cutting edge of human knowledge, to the boundaries of what we understand about reality. One possibility is that planet-sized atoms would exist in a kind of middle ground, showing some quantum properties but not others. Perhaps the electrons would still be restricted to discrete orbitals, maintaining the stability of the atom, but would have more definite positions within those orbitals. Perhaps entanglement would persist but be weaker, allowing for some quantum correlations but not the perfect correlations of smaller systems. Or perhaps planet-sized atoms would reveal new physics entirely, phenomena that only appear at that scale. Just as relativity only becomes important at high speeds, and quantum mechanics only at small scales, there might be new principles that only manifest at the scale of planet-sized atoms. These atoms might be windows into a deeper level of reality, showing us aspects of the universe that are hidden at both smaller and larger scales. As we contemplate these possibilities, it's worth remembering that atoms, even normal-sized atoms, are already deeply mysterious. We use them every day, our bodies are made of them, all of chemistry and biology depends on them, and yet we still don't fully understand them. The fact that electrons don't fall into the nucleus, the fact that atoms are stable, the fact that they can bond together to form molecules, these are miracles that we've gotten used to, mysteries that we've papered over with equations and models. The inside of an atom is not a place in any conventional sense. It's a mathematical space, a realm of probability and possibility, where the usual rules of location and movement don't apply. When we imagine planet-sized atoms, we're not just imagining bigger atoms, we're imagining vast spaces filled with quantum uncertainty, enormous volumes where the bizarre rules of quantum mechanics hold sway. Think about what it would be like to exist inside such an atom. Not to visit it or observe it from outside, but to actually be there, surrounded by the probability clouds of electrons, immersed in the quantum fields that hold the atom together. You wouldn't see electrons zipping past like tiny planets. Instead, you might perceive something like weather, regions of greater and lesser electron probability drifting past like clouds. The nucleus wouldn't be a solid ball, but a seething quantum foam of quarks and gluons, held together by forces so strong they defy everyday description. The colours in this quantum world would be unlike anything in our experience. Not the colours of reflected light, but the intrinsic colours of quantum transitions, the pure frequencies of electron jumps between orbitals. These colours wouldn't mix like paint or light, each would be distinct, monochromatic, perfect. A sodium atom would be pure yellow, not the yellow of a banana or the sun, but the exact frequency of 589 nanometers, scaled up to whatever the appropriate frequency would be for a planet-sized atom. Time itself might flow differently inside a planet-sized atom. Quantum mechanics suggests that time and energy are related by uncertainty. The more precisely you know the energy of a system, the less precisely you can know when events occur. In the discrete energy levels of an atom, time might become fuzzy, uncertain, more like a probability distribution than a steady flow. Events wouldn't happen at specific moments but would be smeared out over time, past and future blending together in quantum superposition. This temporal uncertainty would be particularly pronounced during quantum transitions, when electrons jump between orbitals. During these transitions, the atom exists in a superposition of states, neither in the initial orbital nor the final one, but somehow in both, and neither at the same time. In a planet-sized atom, these transitions might last for years or decades, vast periods of quantum uncertainty where the atom's state is fundamentally indefinite. And yet, despite all this strangeness, all this uncertainty and superposition and entanglement, atoms are the foundation of everything solid and reliable in our world. The chair you're sitting on, the air you're breathing, the neurons firing in your brain as you contemplate these ideas. All of them are made of atoms, these tiny clouds of quantum possibility that somehow add up to classical certainty. This is perhaps the deepest mystery of all. How does the solid, definite world of our experience emerge from the fuzzy, probabilistic world of atoms? How do billions of uncertain quantum states add up to a certain classical state? How does the weirdness of the atomic world disappear when we zoom out to our human scale? Planet-sized atoms, if they existed, might help us answer these questions. They would be large enough that we could see quantum effects directly, without microscopes or particle accelerators. We could watch electron clouds shift and reshape, see quantum jumps happen in real time, observe entanglement and superposition on a scale we could comprehend. They would be like natural laboratories for studying the quantum classical transition, showing us how the weird becomes normal, how uncertainty becomes certainty. As we prepare to leave the inside of the atom and return to larger scales, let's take one last look around this quantum realm. See how empty it is, but how that emptiness is full of potential. See how uncertain everything is, but how that uncertainty allows for stability. See how strange the rules are, but how those strange rules give rise to all the familiar phenomena of our world. The atom is not a thing but a process, not a structure but a dance, not a being but a becoming. It exists in the constant tension between what is and what might be, between the actual and the potential, between the classical and the quantum. And if atoms could be the size of planets, these tensions would play out on a cosmic scale, turning the universe into a vast quantum theatre where the fundamental mysteries of existence are enacted for all to see. In the next phase of our journey, we'll take this understanding of what atoms are and begin to imagine what would happen if we could somehow expand them, stretch them, inflate them like balloons until they rival planets in size. We'll explore what science tells us about the limits of atomic size and what might happen if we could somehow transcend those limits. We'll venture into the realm of Rydberg atoms, those giants of the atomic world that hint at the possibility of even larger atoms, and we'll see how far we can push the boundaries of the possible before they break entirely. Now we begin our main thought experiment in earnest, the gentle stretching of reality that will take us from the world we know into realms of pure imagination. But we won't rush this transformation. Like a glassblower working with molten glass, slowly and carefully shaping it into something new, we'll take our time expanding atoms from their natural microscopic size to the scale of worlds. And as we do, we'll discover that nature herself has already begun this experiment for us, creating atoms so large they challenge our understanding of what an atom can be. Let me tell you about something remarkable that scientists have actually created in laboratories around the world: Rydberg atoms. These are real atoms, not theoretical constructs or mathematical abstractions, but actual atoms that have been coaxed into swelling to enormous sizes, at least by atomic standards. Named after the Swedish physicist Johannes Rydberg, who studied their spectral lines, these atoms represent nature's own attempt at creating giant atoms, and they give us a glimpse of what might be possible if we could push atoms even further. In a Rydberg atom, one electron has been excited to a very high energy level, very far from the nucleus. Imagine taking a normal hydrogen atom and adding energy to it, pumping it up like inflating a balloon. The electron absorbs this energy and jumps to higher and higher orbitals, each one larger than the last. In a normal hydrogen atom, the electron in its ground state orbits at about 0.05 nanometers from the nucleus. But in a Rydberg atom with the electron in the N100 energy level, where n is the principal quantum number, the electron can be found as far as 0.5 micrometers from the nucleus, 10,000 times farther away. These Rydberg atoms are giants in the atomic world. The largest ones created in laboratories can be almost a millimeter across, large enough that you could theoretically see them with the naked eye if they emitted enough light. They're so large that they overlap with neighbouring atoms, their electron clouds interpenetrating in ways that normal atoms never could. They're so large that they can contain other normal atoms within their electron clouds, like cosmic nesting dolls with atoms inside atoms. But Rydberg atoms are also incredibly fragile, delicate structures that can be disrupted by the slightest disturbance. A tiny electric field, a weak magnetic field, even the blackbody radiation from the walls of the container can be enough to ionize a Rydberg atom, stripping away its distant electron. They can only exist in extremely controlled conditions, in ultra-high vacuum chambers at temperatures near absolute zero, isolated from all external influences. They're like soap bubbles in the atomic world, beautiful and ephemeral, existing only for microseconds or milliseconds before they decay back to lower energy states or lose their electrons entirely. What makes Rydberg atoms so fascinating for our thought experiment is that they show us how the properties of atoms change as they get larger. The electron in a Rydberg atom moves much more slowly than in a normal atom, taking milliseconds to orbit the nucleus instead of femtoseconds. The binding energy holding the electron to the nucleus is incredibly weak, thousands of times weaker than in a ground state atom. The atom becomes sensitive to effects that normal atoms completely ignore, like the gravitational pull of nearby masses or the magnetic field of the Earth. As we imagine scaling atoms up even further, from the millimeter size of the largest Rydberg atoms to the planetary scale of our thought experiment, these trends would continue and amplify. The electron would move even more slowly, perhaps taking years or centuries to complete an orbit. The binding energy would become even weaker, so weak that the gravitational pull of nearby stars might be enough to strip electrons away. The atom would become sensitive to cosmic influences, responding to the gravitational waves from distant black hole mergers or the magnetic fields of entire galaxies. But let's think carefully about what we mean when we say we're scaling up an atom. Are we simply making everything bigger, keeping all the proportions the same? Are we changing the fundamental constants of nature to allow for larger atoms? Or are we imagining something else entirely, a new kind of structure that resembles an atom but operates on different principles? If we simply scaled up an atom, making everything larger but keeping the same proportions and forces, we would quickly run into problems. The electromagnetic force that holds electrons to nuclei follows an inverse square law. It gets weaker with distance. If we made an atom 1 billion times larger, the force between the nucleus and electron would be 1 billion times weaker. The electron wouldn't be bound at all, it would simply drift away into space. To have a stable planet-sized atom, we would need to change something fundamental about how forces work or what's providing the binding. One possibility is that in our planet-sized atoms, gravity becomes the binding force instead of electromagnetism. After all, planets are held in orbit around stars by gravity, not electromagnetic forces. Perhaps our planet-sized atoms are really gravitational atoms, with massive particles orbiting around even more massive centers, held in place by the curvature of space-time rather than the exchange of photons. Such gravitational atoms wouldn't be completely hypothetical. Physicists have seriously considered whether black holes could have hair, quantum states analogous to electron orbitals but for gravitational fields, and in some theories of quantum gravity, there might be gravitational bound states, objects held together by quantum gravitational effects. Our planet-sized atoms might be examples of such exotic objects, operating on principles we haven't discovered yet because we've never been able to study quantum gravity directly. Another possibility is that our planet-sized atoms use a different force entirely, something beyond the 4 fundamental forces we know about: gravity, electromagnetism, and the strong and weak nuclear forces. Perhaps there's a 5th force that only becomes significant at very large scales, a force that we haven't detected because it's too weak at the scales we can study. This force might allow for stable structures at planetary scales that resemble atoms in their quantum properties, but operate on completely different principles. Or perhaps the scaling isn't uniform. Maybe the nucleus of our planet-sized atom isn't scaled up proportionally, but remains relatively small, while only the electron orbitals expand to planetary size. This would be more like an extreme Rydberg atom, with electrons orbiting at enormous distances from a relatively tiny nucleus. The nucleus might be the size of a mountain or a small moon, incredibly dense, possibly made of exotic matter like quark matter or strange matter, while the electrons orbit at distances of thousands or millions of kilometers. Let's explore this possibility further. Imagine a nucleus the size of Mount Everest, about 10 kilometers across, but with the mass of a small star, perhaps 1/10 of our Sun's mass. This nucleus would be incredibly dense, denser than a neutron star, held together by forces we don't fully understand. Around this ultra-dense core, electrons orbit at distances comparable to planetary orbits. The innermost electron might orbit at the distance of Mercury from our Sun, while outer electrons could be as far away as Jupiter or Saturn. These electrons wouldn't be point particles but would be spread out in vast probability clouds, just like in normal atoms, but on an enormous scale. The one's orbital, the innermost electron cloud, might be a sphere 100 million kilometers across, filled with a thin haze of electron probability. You could fly a spaceship through this cloud, and you'd have some tiny chance of interacting with the electron, but most likely you'd pass through without noticing anything except perhaps a slight change in the local electric field. The electron clouds of our planet-sized atom would overlap and interpenetrate, creating complex three-dimensional patterns of probability density. The p orbitals would be vast dumbbell shapes, hundreds of millions of kilometers long. The d and f orbitals would have even more complex shapes, with multiple lobes and nodes creating intricate patterns in space. These patterns would be invisible to the naked eye, but if we could somehow make them visible, they would be among the most beautiful structures in the universe, vast three-dimensional standing waves of quantum probability. As we continue to imagine these planet-sized atoms, we need to consider what would happen when they interact with light. In normal atoms, photons are absorbed and emitted when electrons jump between energy levels. The energy of the photon must exactly match the energy difference between the levels, which is why atoms can only absorb and emit specific colors of light. In our planet-sized atoms, the energy levels would be much closer together because the electrons are farther from the nucleus and less tightly bound. This means our planet-sized atoms would interact with much lower energy photons, perhaps in the radio or microwave part of the spectrum rather than visible light. When an electron jumped from one orbital to another, it might emit radio waves that could be detected from across the galaxy. The atom would be like a natural radio transmitter, broadcasting its quantum transitions to the universe. Different elements would broadcast at different frequencies, creating a cosmic symphony of radio emissions. But the slow pace of everything in planet-sized atoms would mean these transitions would take a very long time. In a normal atom, an electron can jump between orbitals in femtoseconds. In our planet-sized atom, the same transition might take years or decades. The atom would slowly brighten in radio waves as the electron prepared to jump, then suddenly emit a burst of radiation as the transition occurred, then slowly fade as the electron settled into its new orbital. This brings us to an interesting question about time and scale. In our thought experiment, we've been assuming that time flows at the same rate for planet-sized atoms as for normal atoms. But what if time itself scaled with size? What if processes in planet-sized atoms happened at the same rate relative to their size as in normal atoms? In this case, an electron orbit that takes a femtosecond in a normal atom might still take a femtosecond in a planet-sized atom, but a femtosecond in that scaled-up world might correspond to millions of years in our world. This idea of scaled time isn't completely arbitrary. In relativity, time is not absolute, but depends on gravity and velocity. Near a massive object, time runs slower. If our planet-sized atoms had enormous mass concentrated in their nuclei, time would run slower near the nucleus than far away. An electron falling toward the nucleus would experience time dilation, its clock running slower as it approached the intense gravitational field. This would add another layer of complexity to the quantum mechanics of these atoms, mixing quantum effects with relativistic effects in ways we've never seen before. Let's imagine actually visiting one of these planet-sized atoms, approaching it in a spaceship from deep space. From a distance, you might not see anything at all, just empty space. But as you got closer, your instruments would start detecting something strange. Fluctuations in the electric and magnetic fields, patterns that seemed random at first but gradually revealed an underlying order. You'd be entering the outermost electron clouds, regions where the probability of finding an electron is very low but not zero. As you continued inward, the field fluctuations would become stronger and more regular. You might start to see something like an aurora, a faint glow as your spaceship interacted with the electron probability clouds. The glow would be strongest in certain regions and completely absent in others, corresponding to the nodes and antinodes of the electron orbitals. You'd be flying through a three-dimensional standing wave pattern, frozen in space but shimmering with quantum uncertainty. If you could somehow see the electron itself, which you couldn't, because the act of seeing would disturb its quantum state, it wouldn't look like a tiny particle zipping around. Instead, it might appear as a ghostly presence, sometimes more concentrated in one region, sometimes in another, never quite solid, never quite absent. It would be like trying to photograph a ghost that exists in multiple places at once, each photograph showing it in a different location, but no single photograph capturing its true nature. The nucleus of our planet-sized atom would be a different kind of spectacle entirely. If it were the size of a mountain but with the mass of a star, the gravitational field near it would be intense. Space-time would be visibly warped, light bending as it passed close to the nucleus. If the nucleus were rotating, it would drag space-time around with it, creating a gravitational vortex that would affect everything nearby. The combination of electromagnetic and gravitational effects would create phenomena we've never seen before, a mixture of quantum mechanics and general relativity that physicists have long dreamed of studying. But perhaps the most remarkable thing about planet-sized atoms would be their chemistry. How would these giant atoms bond together to form molecules? In normal chemistry, atoms share or exchange electrons to form bonds, creating molecules that are only slightly larger than the constituent atoms. But if atoms were planet-sized, molecular bonds would span interstellar distances. Two planet-sized hydrogen atoms bonding to form H2 would create a molecule the size of a solar system, with the two nuclei orbiting their common center of mass and sharing a vast cloud of electron probability. Chemical reactions between planet-sized atoms would be cosmic events. When two atoms approached each other, their electron clouds would begin to overlap when they were still millions of kilometers apart. The clouds would distort and reshape, the electrons rearranging themselves to minimize energy. If the conditions were right for a bond to form, the atoms would slowly spiral toward each other, their electron clouds merging into new molecular orbitals. The process might take millions of years, a slow-motion dance of quantum probability clouds gradually finding their optimal configuration. And what about more complex molecules? A planet-sized water molecule, with one oxygen and two hydrogen atoms, would be a structure hundreds of millions of kilometers across. The bent shape of the water molecule, which gives water many of its unique properties, would be preserved but on an enormous scale. You could travel from one hydrogen atom to another, a journey that might take years even at the speed of light, all while remaining within a single molecule. Organic chemistry at this scale becomes almost unimaginable. A single protein molecule made of planet-sized atoms would be larger than our entire solar system, possibly larger than the distance to the nearest star. DNA, with its double helix of billions of atoms, would be a structure spanning light years, a cosmic spiral containing the information needed to build. What kind of life could exist at such scales? This brings us to one of the most profound questions raised by planet-sized atoms. Could they support complexity, and perhaps even life? In our world, life depends on chemistry, on the ability of atoms to form complex molecules that can store information, catalyze reactions, and reproduce themselves. If atoms were planet-sized, could similar complexity arise, just on a vastly larger scale and slower timescale? The challenge is time. If chemical reactions between planet-sized atoms take millions of years, how long would biological processes take? A single generation of reproduction might take billions of years. Evolution, which requires many generations of variation and selection, might take longer than the current age of the universe. By the time such life evolved to complexity, the stars might have all burned out, leaving the universe cold and dark, unless, of course, time itself works differently for planet-sized atoms. If there's a way for processes to happen faster relative to the size of the atoms, perhaps through quantum effects we don't yet understand, then complexity and even life might be possible. The beings that evolved from planet-sized atoms would be vast and slow by our standards, but they might experience time the same way we do, with thoughts and experiences happening at a subjective rate similar to ours. As we push our imagination further, we might wonder whether there's a limit to how large atoms can be, even in principle. We've talked about planet-sized atoms, but why stop there? Could there be star-sized atoms, galaxy-sized atoms, universe-sized atoms? Is there some fundamental limit that prevents atoms from being arbitrarily large? In our current understanding of physics, there are several limits. The uncertainty principle relates the size of an orbital to the momentum of the electron. Larger orbitals require smaller momenta, and there's a limit to how small the momentum can be. The speed of light limits how quickly information can travel across an atom. If an atom were too large, it couldn't maintain quantum coherence. Decoherence from interaction with the environment becomes more likely as systems get larger. A planet-sized atom would be constantly bombarded by photons, cosmic rays, and gravitational waves that would disrupt its quantum state. But these limits are based on physics as we know it. In a universe with different fundamental constants, or with additional forces we haven't discovered, the limits might be different. Perhaps there are ways to shield large atoms from decoherence, to maintain quantum coherence across vast distances, to allow for stable structures at scales we can't currently imagine. One intriguing possibility is that planet-sized atoms might not be stable in isolation, but could be stabilized by their environment. Just as normal atoms in a solid are stabilized by their interactions with neighboring atoms, planet-sized atoms might be stabilized by their interactions with the cosmic environment. They might exist only in special regions of space, where conditions are just right, where the balance of forces and fields allows for these enormous quantum structures to persist. These special regions might be near black holes, where the intense gravitational field could provide the binding force for planet-sized atoms, or they might be in the vast voids between galaxies, where the low density of matter and radiation allows quantum coherence to persist over large scales. Or they might be in the early universe, when conditions were very different from today, when the fundamental forces had different strengths and atoms could naturally grow to enormous sizes. This last possibility is particularly intriguing. In the very early universe, just after the Big Bang, the fundamental forces were unified, and the laws of physics were different from what we see today. As the universe cooled and expanded, the forces separated and took on their current forms. But what if, during this transition, there was a brief period when atoms could be much larger than they are today? What if planet-sized atoms actually existed in the early universe? Fossils from a time when physics itself was different. These primordial planet-sized atoms would have been unstable in the current universe, decaying as conditions changed and the fundamental constants shifted to their present values. But perhaps some remnant of them remains, some trace that we could detect if we knew what to look for. Perhaps the cosmic microwave background radiation, the afterglow of the Big Bang, contains subtle patterns that reflect the existence of planet-sized atoms in the early universe. Perhaps some of the mysterious dark matter that makes up most of the mass of the universe consists of remnants of these primordial giant atoms, stripped of their electrons and compressed into exotic forms we don't yet understand. As we contemplate these possibilities, we're pushing the boundaries not just of atomic size but of physics itself. We're imagining not just larger atoms but different kinds of atoms, structures that challenge our fundamental understanding of matter and energy, space and time, the quantum and the classical. We're using the simple question, what if atoms could be bigger than planets, as a key to unlock deeper questions about the nature of reality itself. There's an old saying that history doesn't repeat itself, but it rhymes. The same might be said of the universe at different scales. As we look from the tiniest particles to the larger structures, we see patterns that echo and resonate, similar forms appearing again and again like themes in a cosmic symphony. The spiral of a galaxy mirrors the spiral of a hurricane, which mirrors the spiral of a nautilus shell, which mirrors the spiral of DNA. These patterns aren't identical, but they rhyme, suggesting deep principles that transcend any particular scale. Tonight, as we contemplate planet-sized atoms, we're exploring one of the most striking rhymes in nature, the similarity between atoms and solar systems. Both have dense centers surrounded by lighter objects in motion. Both are mostly empty space. Both are held together by fundamental forces that decrease with distance. Both have stable configurations and unstable ones, allowed orbits and forbidden ones. The resemblance is so striking that for decades after the discovery of atomic structure, scientists and science fiction writers imagined that atoms might literally be tiny solar systems, with electron planets orbiting nuclear suns. We now know this picture is wrong in important ways. Electrons don't orbit nuclei the way planets orbit stars. Quantum mechanics, not classical mechanics, governs the atomic world, and yet the rhyme persists, deeper and more subtle than a simple visual analogy. There are profound similarities between atomic and astronomical systems, similarities that might tell us something fundamental about how nature organizes matter and energy across vastly different scales. Let's start with the most obvious similarity, the concentration of mass at the center. In our solar system, 97.86% of the total mass is in the Sun, with the planets, moons, asteroids and comets making up just 0.1%. Similarly, in an atom, more than 99.94% of the mass is in the nucleus, with the electrons contributing less than 0.06%. This concentration of mass creates a strong central force field, gravitational in the case of solar systems, electromagnetic in the case of atoms, that dominates the dynamics of the entire system. but the similarity goes deeper than just mass distribution. Both atoms and solar systems have discrete stable configurations. Planets can't orbit at arbitrary distances from the Sun. There are stable orbits and unstable ones, regions where planets can persist for billions of years, and regions where they would quickly be ejected or spiral into the Sun. Similarly, electrons can't orbit at arbitrary distances from the nucleus. They must occupy specific orbitals determined by quantum mechanics, with gaps between them where electrons cannot exist. This discreteness, this quantization of allowed states, appears to be a fundamental feature of nature. It shows up not just in atoms and solar systems, but in many other contexts. Vibrating strings have discrete harmonics. Water waves in a circular tank have discrete patterns. Even the universe itself might be quantized, with space and time coming in discrete indivisible units at the Planck scale. The rhyme between atoms and solar systems might be part of a larger pattern, a universal tendency toward discrete, stable configurations in any system with a central force. The shapes of orbitals and orbits also rhyme in interesting ways. The simplest electron orbital, the s orbital, is spherical, with the electron equally likely to be found in any direction from the nucleus. The simplest planetary orbit is circular, or nearly so, with the planet maintaining a constant distance from the star. Both represent the lowest energy, most stable configuration, the ground state of the system. As we go to higher energy states, the shapes become more complex. The p orbitals have a dumbbell shape, with two lobes on opposite sides of the nucleus. Similarly, highly elliptical planetary orbits have two distinct regions: the perihelion, where the planet is close to the star and moving quickly, and the aphelion, where it's far away and moving slowly. The d and f orbitals have even more complex shapes with multiple lobes, and we can imagine, though we don't see in our solar system, planetary orbits with complex resonances that trace out intricate patterns over time. There's also a similarity in how these systems respond to perturbations. When an atom absorbs energy, an electron jumps to a higher orbital farther from the nucleus. When a planet gains energy, perhaps from a gravitational interaction with another planet, it moves to a higher orbit, farther from the star. In both cases, adding energy moves things outward, while removing energy causes them to fall inward. This is the universal behavior of bound systems, whether bound by gravity, electromagnetism, or any other attractive force. But perhaps the most profound rhyme between atoms and solar systems is in their stability mechanisms. Both systems are stable because of a balance between attractive and repulsive effects. In solar systems, gravity pulls planets toward the star, but their angular momentum keeps them in orbit, creating an effective outward force, centrifugal force, that balances gravity. In atoms, electromagnetic attraction pulls electrons toward the nucleus, but quantum mechanics provides a kind of pressure, related to the uncertainty principle, that prevents them from falling all the way in. This balance is delicate and can be disrupted. If a planet loses too much angular momentum, it spirals into its star. If it gains too much energy, it escapes to interstellar space. Similarly, if an electron loses too much energy, it falls to a lower orbital, though it can't fall below the ground state. If it gains too much energy, it escapes the atom entirely, leaving behind an ion. Now, let's imagine what happens when we scale up atoms to planetary size. Do they become more like solar systems, or do they remain fundamentally quantum mechanical? The answer might be both. Our planet-sized atoms might exist in a middle ground, showing some properties of solar systems and some properties of atoms, a hybrid that reveals new aspects of both. In our planet-sized atom, the electron wouldn't orbit like a planet, following a definite elliptical path. It would still exist as a probability cloud, but this cloud would be enormous, perhaps the size of our entire solar system. Yet because of the atom's size, we might be able to see wave-like properties that are invisible in normal atoms. The electron's wave function might create standing wave patterns in space, visible as variations in density or electromagnetic fields, like cosmic aurora spanning millions of kilometers. These standing waves would be three-dimensional, creating complex interference patterns throughout the volume of the atom, where waves constructively interfere, the probability of finding the electron would be high. Where they destructively interfere, creating nodes, the probability would be zero. A spaceship traveling through a planet-sized atom would experience regions of intense electromagnetic activity, alternating with regions of perfect calm, a three-dimensional maze of quantum probability. The discrete energy levels of the planet-sized atom would create a kind of cosmic music. Just as a vibrating string produces discrete harmonics, integer multiples of a fundamental frequency, our planet-sized atom would have discrete energy levels that form a harmonic series. If we could somehow hear the electromagnetic emissions from these atoms, they might sound like cosmic chords, harmonious combinations of frequencies that reflect the mathematical beauty of quantum mechanics. But let's push this musical analogy further. In our solar system, the planets orbit with different periods that occasionally align, creating what astronomers call conjunctions. When Jupiter and Saturn align, for example, their combined gravitational effect can perturb the orbits of other planets and asteroids. These alignments happen periodically, creating rhythms and cycles in the solar system's dynamics. In our planet-sized atoms, similar alignments might occur. If an atom had multiple electrons in different orbitals, their probability clouds would overlap and interfere, creating periodic patterns of constructive and destructive interference. These patterns would evolve over time as the phase relationships between different orbitals changed, creating a kind of quantum choreography, a dance of probability waves that might be the most beautiful thing in the universe if we could see it. The interaction between multiple planet-sized atoms would add another layer of complexity. When two atoms approach each other, their electron clouds would begin to overlap while they're still millions of kilometers apart. The overlapping clouds wouldn't just add together, they would interfere, creating new patterns, new standing waves that encompass both atoms. This is how chemical bonds form, through the overlap and interference of electron orbitals, but at the scale of planet-sized atoms, we could watch it happen in slow motion over millions of years. Imagine two planet-sized hydrogen atoms slowly approaching each other, destined to form a planet-sized H2 molecule. At first, they're independent, each with its own spherical electron cloud. But as they get closer, the clouds begin to distort, reaching out toward each other like cosmic hands preparing to clasp. The region between the atoms becomes denser with electron probability, while the regions on the far sides become more sparse. The atoms are no longer spherical but elongated, stretched by their mutual attraction. As the atoms continue to approach, something remarkable happens. The two separate electron clouds merge into a single molecular cloud that encompasses both nuclei. This isn't just a mixing or averaging. It's a quantum mechanical transformation that creates new molecular orbitals, new patterns of electron probability that didn't exist in either atom alone. The bonding orbital, where the electrons are most likely to be found, forms a dense bridge between the nuclei, holding them together. The anti-bonding orbital, where electrons are unlikely to be found, creates a node, a region of zero probability, perpendicular to the bond axis. This molecular formation would be visible as a vast restructuring of space itself, at least in terms of electromagnetic fields and quantum probability. Spacecraft traveling through the region would experience the transformation, feeling the changing fields, perhaps seeing aurora-like displays as charged particles interacted with the evolving electron clouds. It would be like watching the birth of a new cosmic structure, a quantum mechanical sculpture the size of a solar system. But molecules made of planet-sized atoms wouldn't just be static structures. They would vibrate and rotate just like normal molecules, but on enormous scales. A planet-sized H2 molecule would vibrate with the two nuclei moving closer together and farther apart, oscillating with a period of perhaps thousands of years. The molecule would also rotate, spinning around its center of mass with a period of millions of years. These motions would be quantized, only certain vibrational and rotational states allowed, just as in normal molecules. The spectroscopy of planet-sized molecules would be extraordinary. When a molecule transitions between rotational or vibrational states, it emits or absorbs photons with very specific energies. For planet-sized molecules, these photons would be in the radio or microwave part of the spectrum, with wavelengths of kilometers or thousands of kilometers. A single molecular transition might release as much energy as a nuclear bomb, but spread out over such a large volume that it would appear as a gentle glow rather than an explosion. Now let's consider what happens when we have many planet-sized atoms together, perhaps forming a solid or liquid. In normal matter, atoms are packed closely together, their electron clouds overlapping significantly. In a metal, the outermost electrons are completely delocalized, free to move throughout the entire material, which is why metals conduct electricity. In a planet-sized solid, these effects would be magnified enormously. Imagine a crystal made of planet-sized atoms, perhaps a diamond where each carbon atom is the size of Earth. The crystal structure would span light years, a vast three-dimensional lattice with perfect geometric regularity. The bonds between atoms, normally just a few angstroms long, would be millions of kilometers long, yet they would still be quantum mechanical, still governed by the overlap of electron orbitals. In such a crystal, electrons could be delocalized over astronomical distances. An electron, and wouldn't belong to any particular atom, but would be spread throughout the entire crystal, its wave function extending over light years. This would be a kind of quantum coherence on a cosmic scale, a single quantum state encompassing a volume larger than our solar system. The entire crystal would be, in a sense, a single quantum object, despite its enormous size. The properties of such a crystal would be unlike anything in our experience. It might be superconducting, carrying electrical current with zero resistance over interstellar distances. It might be superfluid, flowing without friction around obstacles the size of planets. It might exhibit quantum phenomena that we've never seen because they only emerge at such large scales, new phases of matter that require both quantum mechanics and general relativity to describe. But there's another way that atoms and solar systems rhyme that we haven't explored yet: their formation. Solar systems form from collapsing clouds of gas and dust, with gravity pulling material inward while conservation of angular momentum causes it to spin faster and flatten into a disk. Planets form from this disk through accretion, small particles sticking together to form larger and larger bodies. The process is hierarchical, building from small to large over millions of years. Atoms, in contrast, don't form this way in our universe. They're created in the extreme conditions of the Big Bang or in the cores of stars, where nuclear fusion combines protons and neutrons into nuclei, which then capture electrons to become atoms. But what if planet-sized atoms could form through a process more like planetary formation? Imagine a vast cloud of subatomic particles, protons and neutrons and electrons, spread over a volume the size of a galaxy. Under the right conditions, perhaps in the presence of some exotic force or field, these particles might begin to condense, not into normal atoms, but directly into planet-sized atoms. The protons and neutrons would cluster together, forming a massive nucleus, while the electrons would settle into vast orbital clouds around them. This process might be incredibly slow, taking billions of years for a single planet-sized atom to form. But once formed, these atoms might be stable for even longer periods, perhaps for trillions of years, slowly evolving and interacting with their environment. They might capture additional particles, growing larger over time, or they might decay, shedding electrons and eventually breaking apart. The life cycle of planet-sized atoms might rhyme with the life cycle of stars. Just as stars are born from gas clouds, live for millions or billions of years burning nuclear fuel, and eventually die in supernovae or fade away as white dwarfs, planet-sized atoms might have their own births, lives, and deaths. They might have their own kinds of nuclear processes, their own ways of generating energy, their own spectacular death throes. In fact, planet-sized atoms might be the stars of their universe, the primary sources of energy, and the crucibles where heavier elements are formed. Just as stars in our universe create heavy elements through nuclear fusion, planet-sized atoms might create new kinds of matter through quantum processes we can't imagine. They might be the engines that drive the evolution of their universe, the sources of complexity and eventually life. This brings us back to the question of scale and hierarchy in the universe. We tend to think of atoms as fundamental, elementary, the building blocks from which everything else is made. But what if that's just our perspective, our position in the hierarchy? What if, from a different vantage point, atoms are complex structures made of simpler components, which are themselves made of even simpler components, in an infinite regression of scales? Some theories in physics actually suggest something like this. String theory, for example, proposes that what we call elementary particles are actually vibrating strings, and that these strings might themselves be made of more fundamental objects. The holographic principle suggests that our three-dimensional world might be a projection of information stored on a two-dimensional surface. These ideas challenge our notion of what's fundamental and what's emergent, what's elementary and what's composite. Planet-sized atoms fit into this picture as another level in the hierarchy, another scale at which matter organizes itself into complex structures. They might not be fundamental any more than normal atoms are fundamental, but they represent a valid way that matter and energy can be organized, a possible form that the universe can take. As we contemplate these ideas, we're led to an even more amazing possibility. What if our entire universe, everything we can see and detect, is actually a single electron in a planet-sized atom in some larger cosmos? What if the Big Bang was just this electron jumping to a higher orbital, and the expansion of the universe is just the electron cloud spreading out to fill its new, larger orbital? What if dark energy, the mysterious force causing the universe to expand faster and faster, is just the quantum pressure that keeps the electron from falling back to a lower orbital? This idea might seem like pure fantasy, but it's actually been seriously considered by physicists. The observable universe has some properties that are surprisingly atom-like. It's finite in size but unbounded, like the surface of a sphere. It's expanding from a hot, dense state, like an electron jumping to a higher energy level. It has a discrete spectrum of fluctuations in the cosmic microwave background, like the discrete spectrum of an atom. Of course, there are also major differences. The universe doesn't seem to be repeating or cyclic in the way we'd expect if it were truly an electron orbital. The expansion of the universe is accelerating, which doesn't match the behavior of electrons in atoms, and we haven't detected any signs of a cosmic nucleus that our universe electron is orbiting around. But perhaps these differences just reflect our limited perspective. Perhaps the universe's electron operates on timescales so vast that we haven't observed a complete orbital period yet. Perhaps the cosmic nucleus is hidden beyond our observable horizon, or in dimensions we can't perceive. Perhaps the acceleration of the universe's expansion is leading up to a quantum jump to an even higher orbital, a cosmic transition that will transform everything we know. These ideas stretch our imagination to its limits and beyond. We're no longer just thinking about planet-sized atoms, but about universe-sized atoms, cosmos-sized atoms, structures so vast that our entire reality is just a tiny component. We're contemplating the possibility that the hierarchy of scales extends infinitely in both directions, that there's no bottom and no top, just an endless series of structures within structures within structures. As we venture deeper into our exploration of planet-sized atoms, it's time to look at what the actual universe might be telling us about such possibilities. While true planet-sized atoms as we've imagined them don't exist in nature as far as we know, the cosmos has created some remarkable objects that share certain properties with our imaginary giant atoms. These objects, exotic and extreme, push the boundaries of matter and force us to reconsider what's possible at the intersection of quantum mechanics and gravity. Let me tell you about neutron stars, perhaps the closest things in the real universe to giant atomic nuclei. When a massive star reaches the end of its life and explodes in a supernova, its core can collapse into an object so dense that protons and electrons are crushed together to form neutrons. The result is essentially a giant atomic nucleus, kilometers across but containing more mass than our Sun. A sugar cube-sized piece of neutron star material would weigh about as much as Mount Everest. The entire star is like a single, gigantic nucleus held together not by the strong nuclear force, but by gravity. Neutron stars are typically about 20 kilometers in diameter, but contain between 1.4 and 2 times the mass of our Sun. This means their density is comparable to that of an atomic nucleus, about 1017 kilograms per cubic meter. In a very real sense, a neutron star is what you get when you scale up nuclear matter to macroscopic size. It's not quite a planet-sized atom, but it's a stellar mass nucleus, which is perhaps even more remarkable. The surface gravity on a neutron star is about 200 billion times stronger than Earth's gravity. If you could somehow stand on the surface, which you couldn't, because you'd be instantly crushed into a thin film of subatomic particles, you would weigh 200 billion times what you weigh on Earth. The escape velocity is about 1/3 the speed of light. Space-time is so warped near the surface that time runs, about 30% slower than in deep space. These are conditions where quantum mechanics and general relativity both become important, creating phenomena we're only beginning to understand. But neutron stars aren't just giant nuclei. They have structure and complexity that in some ways resembles atoms. They have a thin atmosphere, perhaps a few centimeters thick, made of normal atoms crushed by the intense gravity. Below this is a crust of crystallized matter, atoms compressed into a solid lattice but still maintaining their identity. Deeper still, the matter becomes increasingly exotic. Atomic nuclei merge into long strings and sheets, forming what physicists call nuclear pasta because of the spaghetti-like and lasagna-like structures. In the core of a neutron star, matter might exist in states we've never seen elsewhere. There might be quark matter, where the neutrons themselves dissolve into their constituent quarks. There might be strange matter, containing strange quarks in addition to the usual up and down quarks. There might even be more exotic possibilities: colour superconductors, crystalline colour superconductors, phases of matter that require new physics to describe. The neutron star, in its compressed immensity, might be a natural laboratory for states of matter that exist nowhere else in the universe. Neutron stars also pulse with radio waves, spinning rapidly and emitting beams of radiation like cosmic lighthouses. These pulsars, as they're called, can rotate hundreds of times per second, their surfaces moving at appreciable fractions of the speed of light. The magnetic fields around neutron stars can be 1 trillion times stronger than Earth's magnetic field, strong enough to distort the shapes of atoms, stretching them into long, thin cylinders aligned with the field. In these extreme magnetic fields, atoms cease to exist in their normal form. The electrons are confined to move only along the magnetic field lines, effectively turning three-dimensional atoms into one-dimensional structures. The energy levels of these distorted atoms are completely different from normal atoms, creating new kinds of chemistry, new possibilities for molecular structure. This is matter in a regime we can barely imagine, where the basic building blocks of chemistry are fundamentally altered. But let's consider an even more exotic possibility: quark stars. These hypothetical objects would be composed entirely of quark matter, a soup of free quarks not confined within individual neutrons or protons. A quark star would be even denser than a neutron star, perhaps only 10 kilometers across but containing several solar masses. It would be, in essence, a single giant particle, a macroscopic manifestation of the strong force that usually operates only at subatomic scales. If quark stars exist, they would represent a kind of scaling up of particle physics to astronomical size. The entire star would be a single quantum object, its quarks forming a collective state that extends over kilometers. It would be like a giant hadron, similar to a proton or neutron but billions of billions of billions of times larger. The properties of such an object would be unlike anything else in the universe, a hybrid of particle physics and astrophysics that challenges our understanding of both. Scientists have actually observed a few neutron stars that might be quark stars. These objects are smaller and denser than typical neutron stars, suggesting they might be made of something more exotic than neutrons. But we can't be sure yet. Distinguishing between a small neutron star and a quark star requires measurements more precise than we can currently make. The question remains open, tantalizing us with the possibility that nature has already created objects that blur the line between particles and stars. Now let's turn to another class of exotic objects that might relate to our planet-sized atoms: boson stars. These are hypothetical objects made not of fermions, particles like electrons, protons, and neutrons that obey the Pauli exclusion principle, but of bosons, particles like photons and hypothetical particles like axions that can all occupy the same quantum state. A boson star would be a gigantic Bose-Einstein condensate, a single quantum state extending over astronomical distances. In a Bose-Einstein condensate, all the particles occupy the same quantum state, moving in perfect synchrony like a cosmic symphony, where every instrument plays exactly the same note. In the laboratory, scientists have created Bose-Einstein condensates of atoms cooled to near absolute zero, clouds of millions of atoms all in the same quantum state. A boson star would be similar but on an enormously larger scale, perhaps the size of a star or even larger, all in a single, coherent quantum state. The existence of boson stars would prove that quantum coherence can be maintained over astronomical distances, one of the key requirements for planet-sized atoms. If bosons can form coherent structures the size of stars, perhaps fermions could too under the right conditions. The universe might be full of giant quantum objects that we haven't recognized because we haven't known what to look for. Some physicists have suggested that dark matter, the mysterious substance that makes up about 85% of the matter in the universe, might consist of boson stars or similar exotic objects. These dark matter bosons would interact only weakly with normal matter, making them invisible to our telescopes, but their gravitational effects would be detectable. Entire galaxies might be surrounded by halos of giant quantum objects, planet-sized or star-sized atoms of a sort, made of particles we haven't yet discovered. This brings us to one of the most intriguing possibilities, that planet-sized atoms might exist but be made of different kinds of particles than normal atoms. Perhaps there are dark atoms made of dark matter particles, with dark protons and dark electrons, following their own version of quantum mechanics. These dark atoms might naturally be much larger than normal atoms, perhaps because the dark electromagnetic force is weaker, or because dark particles are lighter. If dark atoms exist and can be planet-sized, they might be all around us, invisible and intangible, passing through normal matter like ghosts. Our galaxy might be full of planet-sized dark atoms, vast quantum structures that we can't see or touch, but that affect the motion of stars through their gravity. When we look at the rotation curves of galaxies and see that they're spinning too fast, held together by invisible dark matter, we might be seeing the gravitational effects of enormous dark atoms. Let's also consider the fascinating objects known as white dwarfs. These are the remnants of stars like our Sun after they've exhausted their nuclear fuel. A white dwarf is about the size of Earth, but contains about as much mass as the Sun, making it incredibly dense, though not as dense as a neutron star. The matter in a white dwarf is supported against gravity not by thermal pressure, as in a normal star, but by electron degeneracy pressure, a purely quantum mechanical effect. In a white dwarf, atoms are crushed so closely together that their electron clouds overlap completely. The electrons form a degenerate gas, a quantum fluid that fills the entire star. In a sense, a white dwarf is like a single giant atom with a shared electron cloud encompassing trillions of nuclei. It's not quite a planet-sized atom, but it's a planet-sized quantum object, demonstrating that quantum effects can indeed operate on planetary scales. The electrons in a white dwarf behave according to quantum statistics, filling up energy levels just like electrons in an atom, but the atom in this case is the entire star. The pressure that supports the white dwarf against gravity comes from the Pauli exclusion principle, the same quantum rule that prevents electrons in atoms from all falling into the lowest energy level. A white dwarf is, in essence, quantum mechanics made macroscopic, a stellar-scale demonstration of atomic principles. As white dwarfs cool over billions of years, they undergo a remarkable transformation. The carbon and oxygen nuclei in their interiors arrange themselves into a crystalline lattice, forming a diamond the size of Earth. This cosmic diamond isn't just a poetic metaphor, it's a real prediction of physics, and astronomers have found white dwarfs cool enough that their interiors must be crystallizing. These crystallized white dwarfs are perhaps the largest ordered structures in the universe, single crystals thousands of kilometers across. Now, let me tell you about some actual observations that might be relevant to planet-sized atoms. In recent years, astronomers have discovered radio signals from space that behave in puzzling ways. Fast radio bursts, FRBs, are brief, intense pulses of radio waves that last only milliseconds but release as much energy as the sun emits in days. Their origin is still mysterious, with theories ranging from magnetars, neutron stars with extreme magnetic fields, to more exotic possibilities. One intriguing aspect of FRBs is their dispersion measure, the way different frequencies arrive at slightly different times due to interaction with electrons in space. The dispersion suggests these signals have travelled through vast clouds of electrons, but not the kind of electron clouds we see in normal interstellar space. Some physicists have speculated that FRBs might be passing through enormous diffuse structures, perhaps remnants of exotic matter from the early universe. Could these structures be related to planet-sized atoms? It's purely speculative, but imagine if some regions of space contained atoms that had been stretched to enormous size by the expansion of the universe or by passage through regions of altered space-time. These cosmic atoms would be incredibly diffuse, their electrons spread over vast volumes, but they might still maintain some quantum coherence. Radio waves passing through them would be dispersed in characteristic ways, possibly explaining some of the puzzling features of FRBs. Another observational puzzle that might relate to giant atoms is the nature of ultra-high energy cosmic rays. These are particles, mostly protons, that strike Earth's atmosphere with energies millions of times higher than we can achieve in our most powerful particle accelerators. Their origin is unknown, but they must come from incredibly extreme environments, places where particles can be accelerated to nearly the speed of light. One possibility is that these cosmic rays are produced by the decay of exotic, massive particles left over from the early universe. If planet-sized atoms or similar structures existed in the early universe, and some remnants survive to the present day, their decay might produce ultra-high energy particles. A planet-sized atom finally breaking apart after billions of years of stability might release its binding energy in a burst of particles with enormous energies. Let's also consider gravitational waves, ripples in space-time that we've recently learned to detect. The LIGO and Virgo observatories have detected gravitational waves from merging black holes and neutron stars, confirming a major prediction of Einstein's general relativity. But there might be other sources of gravitational waves we haven't detected yet, including exotic objects like boson stars or planet-sized atoms. If planet-sized atoms existed and underwent transitions, jumping between energy levels or forming molecular bonds, they might emit gravitational waves in addition to electromagnetic radiation. These gravitational waves would be incredibly weak, far below our current detection threshold, but they would carry information about quantum processes happening on astronomical scales. Future gravitational wave detectors, perhaps, space-based interferometers thousands of kilometers long, might be able to detect these quantum gravitational signals. The early universe provides another window into the possibility of giant atoms. In the first moments after the Big Bang, the universe was incredibly hot and dense, with all of space filled with a soup of elementary particles. As the universe expanded and cooled, these particles combined into protons and neutrons, and eventually into atoms. But the process wasn't instantaneous. There was a period called the Epoch of Recombination, when atoms were forming but the universe was still partially ionized. During this epoch, about 380,000 years after the Big Bang, conditions might have been right for the formation of exotic atoms much larger than normal. The universe was much smaller then, and the fundamental forces might have had slightly different strengths. Quantum fluctuations, the random variations in density that eventually grew into galaxies and galaxy clusters, might have created regions where atoms could grow to enormous size. These primordial giant atoms, if they existed, would have left their mark on the cosmic microwave background, CMB, the afterglow of the Big Bang that we can still observe today. The CMB has tiny temperature fluctuations that tell us about conditions in the early universe. Some of these fluctuations match our theoretical predictions perfectly, but others remain unexplained. Could some of the anomalies in the CMB be signatures of planet-sized atoms in the early universe? One particular anomaly that has puzzled cosmologists is the cold spot, a region of the CMB that's significantly cooler than expected. Various explanations have been proposed, from a supervoid in the large-scale structure of the universe to the collision of our universe with another universe in a multiverse. But another possibility is that the cold spot is the remnant of a region where exotic matter, perhaps including giant atoms, existed in the early universe. Space missions and observations continue to provide new data that might be relevant to planet-sized atoms. The James Webb Space Telescope, with its unprecedented ability to see the early universe, might detect signatures of exotic matter from the first billion years after the Big Bang. The Gaia mission, mapping the positions and motions of billions of stars, might reveal the gravitational effects of invisible giant atoms in our galaxy. The Event Horizon Telescope, which produced the first image of a black hole, might detect exotic matter falling into black holes. Future missions could be even more revealing. Proposed gravitational wave detectors like LISA, Laser Interferometer Space Antenna, will be sensitive to much lower frequencies than ground-based detectors, potentially detecting gravitational waves from exotic objects throughout the universe. Next-generation telescopes might be able to directly image the quantum properties of matter near black holes, where the extreme conditions might allow for exotic states like planet-sized atoms. Laboratory experiments also provide insights into the possibility of giant atoms. Scientists have created Rydberg atoms with electrons in extremely high energy states, as we discussed earlier. They've also created artificial atoms using quantum dots, tiny structures that confine electrons in ways that mimic atomic behavior, but at much larger scales. These experiments show that atom-like behavior can emerge from various physical systems, not just from protons and electrons. One particularly interesting experiment involves ultra-cold atoms in optical lattices. where lasers create a periodic potential that traps atoms in a regular array. By adjusting the laser parameters, scientists can control the effective mass and interaction strength of the atoms, essentially creating designer quantum systems. In some configurations, these systems behave like giant atoms, with quantum properties extending over macroscopic distances. Another relevant area of research is the study of strongly correlated electron systems, materials where the electrons interact so strongly that they can't be treated as independent particles. In these materials, electrons can form collective states that extend over many atoms, creating emergent properties that don't exist in individual atoms. Some of these states, like the quantum Hall effect, involve electrons forming incompressible fluids with exotic properties. These might be viewed as steps toward planet-sized atoms, showing how quantum coherence can extend over larger and larger scales. Scientists have also discovered materials called topological insulators, which conduct electricity on their surfaces but are insulating in their bulk. The surface electrons in these materials form special states that are protected by topology, the mathematical study of shapes and spaces. These topological states are remarkably robust, maintaining their quantum properties even in the presence of disorder and impurities. If similar topological protection could be achieved at astronomical scales, it might allow for stable planet-sized atoms. The field of quantum information provides another perspective on giant atoms. Quantum computers require quantum coherence to be maintained across many qubits, the quantum equivalent of classical bits. Current quantum computers can maintain coherence across dozens or hundreds of qubits, but future machines might have millions or billions. In a sense, a large quantum computer is like an artificial giant atom, a macroscopic system in a coherent quantum state. Some physicists have proposed that the universe itself might be a giant quantum computer, processing information at the Planck scale. In this view, what we perceive as particles and forces are really computational processes, and atoms are just stable computational structures. Planet-sized atoms might then be larger computational structures, perhaps performing calculations we can't even imagine. As we survey all these possibilities, from neutron stars to dark atoms, from laboratory experiments to cosmological observations, we see that the universe is far stranger and more varied than we might have expected. While we haven't found definitive evidence for planet-sized atoms as we've imagined them, we've found plenty of evidence that exotic forms of matter exist, that quantum effects can operate on macroscopic scales, and that the boundaries between the microscopic and the cosmic are not as firm as they might seem. The search for planet-sized atoms, whether literal or metaphorical, drives us to explore the extremes of physics, the places where our theories are pushed to their limits and sometimes beyond. It forces us to confront the assumptions we make about size and scale, about what's possible and what's not. And it reminds us that the universe is under no obligation to conform to our expectations or limitations. Perhaps planet-sized atoms don't exist in our universe, but the fact that we can imagine them, that we can work out what their properties might be, that we can search for evidence of their existence, tells us something important about both the universe and ourselves. The universe is comprehensible, at least partially, and we have the capacity to comprehend it, to imagine possibilities beyond our direct experience and test them against reality. Now let us turn our imagination inward and ask perhaps the most wondrous question of all. What if you, yourself, were small enough to live inside a planet-sized atom? Not just to observe it from outside, not just to study it with instruments, but to actually exist within it, to call it home, to experience its quantum strangeness as your everyday reality. This isn't just an exercise in fantasy, it's a way of understanding what these giant atoms would really mean, how they would transform not just physics, but existence itself. Imagine waking up one morning to find yourself floating in what seems at first to be empty space, but as your eyes adjust, you realize you're surrounded by something far more mysterious. The darkness around you isn't the darkness of night or the darkness of deep space. It's the darkness of probability, punctuated by strange shifting glows that seem to come from everywhere and nowhere at once. You're inside the electron cloud of a planet-sized hydrogen atom, and the familiar rules of reality no longer apply. The first thing you'd notice is that location has become negotiable. You're not in a specific place the way you're used to being in a place. Instead, you exist in a region of likelihood, a zone where the electron might be found. As you move through this space, you don't travel in straight lines from point A to point B. Instead, you find yourself flowing along probability currents, following paths of greater and lesser likelihood, like a fish swimming through streams of chance. The landscape around you, if you can call it a landscape, would be unlike anything on Earth. There would be no solid ground, no sky, no up or down in any absolute sense. Instead, there would be regions of different probability density, some thick like fog, others thin like high mountain air. These regions wouldn't have sharp boundaries but would fade into each other gradually, one probability landscape morphing smoothly into another. As you explore this strange realm, you'd discover that the electron isn't a thing you can find and point to. It's more like weather, a phenomenon that happens throughout the atom rather than an object that exists in one place. Sometimes the electron weather would be calm, with steady probability distributions that barely change. Other times, it would be turbulent, with probability storms that reshape the entire atom in moments, though moments here might last what we would consider years. The nucleus of your planet-sized atom would be the only solid landmark in this sea of uncertainty. But what a landmark it would be! From your position in the electron cloud, it might appear as a distant sphere, blazing with the strong force that holds its protons and neutrons together. But its apparent size would depend on where you are in the electron cloud. From the outer reaches, it might look like a bright star. From closer in, it might loom like a small moon, its surface seething with quantum fluctuations. Approaching the nucleus would be like descending into higher and higher probability density. The closer you get, the more likely the electron is to be there, and the stranger your experience becomes. Time itself would begin to behave oddly. The uncertainty principle tells us that energy and time are complementary variables. The more precisely one is defined, the less precisely the other can be known. Near the nucleus, where the electron's energy is more precisely defined by its strong attraction to the protons, time becomes fuzzy, uncertain. You might experience moments that stretch and compress, where cause and effect become scrambled, where events happen before their causes or effects precede their events. This isn't time travel in the science fiction sense. It's something stranger, a breakdown of the very notion of temporal sequence. You might remember things that haven't happened yet, or forget things immediately after they occur. Your consciousness itself might fragment across multiple probable timelines, experiencing many possible presents simultaneously. The colours in this quantum world would be pure and mathematical. Not the mixed colours of sunlight reflecting off objects, but the precise frequencies of quantum transitions. When the electron jumps from one orbital to another, the entire atom would flash with monochromatic light, a pure colour that has no earthly equivalent. For a planet-sized hydrogen atom, these flashes might be in the radio or microwave spectrum, invisible to human eyes, but perhaps felt as waves of warmth or coolness washing over you. But let's imagine you've been adapted to perceive these frequencies as colours. The atom would be a symphony of pure hues, each corresponding to a specific energy transition. The Lyman series would paint the atom in what you might perceive as deep violets and blues. The Balmer series would add greens and reds. The Passion series would contribute deeper reds, colours at the edge of perception. Each series would have its own character, its own mood, painting the probability clouds in layers of quantum light. Movement in this world would follow quantum rules. You couldn't simply walk or fly from one place to another. Instead, you'd have to navigate probability currents, finding paths through the atom that respect the quantum mechanical wave functions. Some regions would be forbidden to you, nodes where the probability of finding anything is exactly zero. These would be like invisible walls, impossible to cross, dividing the atom into separate quantum chambers. Other regions would be highways of high probability, paths where movement is easy and natural. These would follow the contours of the atomic orbitals, the SPD and orbitals, that we know from chemistry but experience from within. An s orbital would be like a spherical ocean you could swim through in any direction. A p orbital would be like a dumbbell-shaped tunnel with a forbidden zone in the middle that you'd have to go around. The more complex d and f orbitals would be like three-dimensional mazes, with multiple lobes and nodes creating intricate patterns you'd have to learn to navigate. If your planet-sized atom were more complex than hydrogen, with multiple electrons, the situation would become even more interesting. The electrons wouldn't be separate entities that you could meet and greet. Instead, they would be aspects of a single, multi-electron wave function, their identities blended together by quantum indistinguishability. You might experience this as multiple probability weathers happening simultaneously, overlapping and interfering with each other, creating complex patterns of constructive and destructive interference. In regions where electron wave functions constructively interfere, the probability density would be high, and you might feel a kind of quantum pressure, a thickness to space itself. Where they destructively interfere, creating nodes, you'd find voids, regions you simply couldn't enter, as if space itself were missing there. The entire atom would be like a three-dimensional standing wave pattern, frozen in its overall structure but shimmering with quantum fluctuations at every scale. Communication in this world would be challenging. Sound waves, as we know them, require a medium like air or water, but the inside of an atom is mostly vacuum with probability clouds that are far too diffuse to carry sound. You might communicate through electromagnetic radiation, sending radio waves or light pulses through the probability medium, but these signals would be affected by the quantum nature of the atom, sometimes arriving before they were sent, sometimes arriving multiple times, sometimes not arriving at all. You might develop a quantum language, where meaning isn't carried by specific words or signals, but by probability distributions of possible meanings. A message wouldn't say one thing, but would exist in a superposition of possible meanings until it's received and interpreted, at which point it would collapse into a specific meaning. Conversations would be like quantum measurements, each exchange of information changing the state of the atom itself. If you were to build structures in this planet-sized atom, they couldn't be made of normal matter as we understand it. Instead, you might shape probability itself, creating standing wave patterns that serve as walls and floors, rooms and corridors. These structures would be made of likelihood rather than substance, existing as persistent patterns in the electron wave function. They would be quantum architecture, buildings made of mathematics rather than materials. These probability structures would have their own strange properties. They might be solid to some particles but completely transparent to others. They might exist only when observed, disappearing when no one is looking. They might be bigger on the inside than the outside, or exist in multiple locations simultaneously. The ordinary rules of architecture would be replaced by the rules of quantum mechanics, allowing for impossible buildings that could only exist in the quantum realm. The passage of time in your planet-sized atom would be unlike anything in our macroscopic world. Without the regular cycles of day and night, without the steady ticking of clocks, time would be measured by quantum events. Each transition of the electron between orbitals would mark a quantum moment. The gradual evolution of the wave function would be like the changing of quantum seasons. But these timescales would be vastly different from what we're used to. A single electron transition might take what we would consider years, while the complete evolution of a complex wave function might take millennia. You might experience time dilation effects not from gravity or velocity, but from quantum uncertainty. In regions of high energy uncertainty, time would be precisely defined, flowing steadily and predictably. In regions of precise energy, time would become uncertain, flowing in fits and starts, sometimes fast, sometimes slow, sometimes perhaps even backward. Your subjective experience of time would depend on where you are in the atom and what quantum state you're interacting with. Food and energy in this world would have to come from quantum sources. You might feed on photons, absorbing electromagnetic radiation to power your existence. Or you might tap into the zero-point energy, the quantum fluctuations that fill even empty space. You could harvest energy from electron transitions, positioning yourself to absorb the photons emitted when the electron jumps to a lower orbital. This would be quantum agriculture, farming probability and harvesting uncertainty. But living in a planet-sized atom wouldn't just be about survival. It would be about exploration and discovery. The atom would be a universe unto itself, with endless mysteries to uncover. You might discover that at certain energies, the electron wave function forms patterns you've never seen before, creating new regions of the atom to explore. You might find quantum tunnels, places where you can suddenly appear on the other side of a probability barrier without passing through the space in between. You might encounter quantum entanglement with other atoms, feeling the instant correlations with distant partners. When an electron in a faraway atom changes its spin, you might feel a corresponding change in your atom, a spooky action at a distance that connects you to the wider universe. These entanglement channels might serve as quantum communication links, allowing instant contact with beings in other planet-sized atoms, no matter how far away they are. The boundaries of your atom wouldn't be walls, but gradual transitions where the probability of finding the electron drops towards zero. At these edges, you might encounter the quantum vacuum, not empty space, but a seething foam of virtual particles popping in and out of existence. You might see virtual photons carrying the electromagnetic force, virtual electron-positron pairs, matter and antimatter created from nothing and annihilating back into nothing, virtual quarks and gluons hinting at the strong force that binds the nucleus. Venturing beyond your atom, you might find yourself in the space between atoms, a vast void that's not empty but filled with quantum fields. These fields would extend from every atom, overlapping and interfering, creating a kind of quantum weather system on an enormous scale. You might ride these fields from atom to atom, surfing probability waves across interstellar distances. If your planet-sized atom were part of a molecule, you'd experience chemical bonding from the inside. You'd see electron clouds from different atoms merging and reshaping, creating molecular orbitals that encompass multiple nuclei. The covalent bond wouldn't be a stick connecting balls, as in our simple molecular models, but a transformation of space itself, a region where the distinction between one atom and another breaks down. Living through a chemical reaction would be like experiencing a cosmic catastrophe and rebirth. The stable orbitals you've known would suddenly destabilize. Probability landscapes would shift and flow like quantum lava. New patterns would emerge, new structures would form, and when the reaction is complete, you'd find yourself in an entirely different quantum world, perhaps in a different molecule altogether. But perhaps the most profound aspect of living in a planet-sized atom would be the direct experience of quantum superposition. You wouldn't just know intellectually that the electron is in multiple states at once. You'd feel it, experience it, live it. You might find yourself in multiple locations simultaneously, experiencing different probabilities of existence. Your consciousness itself might exist in superposition, thinking multiple thoughts at once, experiencing multiple emotions simultaneously, being multiple versions of yourself until some measurement or interaction causes you to collapse into a single state. This superposition of consciousness might be disturbing at first, but you might come to find it liberating. Instead of being locked into a single perspective, a single way of being, you could explore multiple possibilities simultaneously. You could be happy and sad at the same time, understand multiple sides of an argument simultaneously, exist in a state of quantum wisdom, where contradictions are not problems to be resolved, but aspects of a deeper truth. The social structures that might develop in planet-sized atoms would be unlike anything in our world. Communities might form around stable probability patterns, with different groups inhabiting different orbitals. There might be s-orbital dwellers who prefer the spherical symmetry of the simplest orbitals, p-orbital nomads who travel along the dumbbell-shaped probability highways, and d-orbital mystics who navigate the complex multi-lobed patterns of the higher orbitals. Conflicts in this world wouldn't be about territory in the traditional sense, but about probability resources. Different groups might compete for regions of high electron probability, where existence is most stable and energy is most abundant. Wars might be fought with quantum weapons that reshape wave functions, creating or destroying orbitals, changing the very landscape of the atom. But cooperation might be equally important. Maintaining stable structures in a quantum world might require constant observation, groups of beings working together to collapse wave functions in useful ways. Societies might develop quantum rituals, coordinated observations that maintain the stability of their probability structures. Culture itself might be quantum mechanical, existing in superposition until observed, at which point it collapses into specific traditions and practices. Art in a planet-sized atom would be probability sculpture, the shaping of wave functions into aesthetically pleasing patterns. Music might be the orchestrated timing of electron transitions, creating rhythms and harmonies in the electromagnetic spectrum. Literature might be the exploration of multiple narrative superpositions, stories that exist in quantum states until read, at which point they collapse into specific tales. Science in this world would be the study of the atom from within, a kind of quantum introspection. Scientists might discover new orbitals, new solutions to the Schrödinger equation that only become apparent from inside. They might find ways to manipulate the atom's quantum state, engineering electron transitions, creating artificial orbitals, perhaps even finding ways to change the effective nuclear charge and transform one element into another. Philosophy in a planet-sized atom would grapple with questions we can barely imagine. What does identity mean when you exist in superposition? What is consciousness when it's spread across a probability cloud? What is death in a world where existence is already probabilistic? These beings might develop quantum philosophies that embrace uncertainty as fundamental, that see superposition not as a problem, but as the natural state of existence. As you spend more time in your planet-sized atom, you might begin to realize that this isn't just a strange place you're visiting, it's a different way of being entirely. The quantum rules that seem so bizarre from our macroscopic perspective would become intuitive, natural, obvious. You'd stop thinking in terms of definite positions and velocities and start thinking in terms of probability amplitudes and wave functions. The classical world you came from would start to seem like the strange place, with its rigid insistence on things being in only one place at a time. As we near the end of our journey through the realm of planet-sized atoms, let's pull back our perspective even further and contemplate one of the most mind-bending possibilities of all, that the universe might be organized in nested hierarchies of scale, with atoms within atoms within atoms, each level containing entire worlds invisible to the others. This isn't just a poetic metaphor, but a serious philosophical and scientific question that touches on the deepest mysteries of existence. Consider for a moment the vast range of scales we've already explored, from subatomic particles to atoms, from atoms to molecules, from molecules to living cells, from cells to organisms, from organisms to planets, from planets to solar systems, from solar systems to galaxies, from galaxies to galaxy clusters, from galaxy clusters to the cosmic web, and finally to the observable universe itself. At each level, we find organized structures that couldn't be predicted from the level below. Quarks give rise to protons, but nothing about quarks themselves suggests the existence of DNA. Atoms form molecules, but nothing about individual atoms predicts the existence of life. This emergence of complexity at different scales suggests something profound about the nature of reality. Perhaps complexity isn't just something that happens to matter. Perhaps it's fundamental to the structure of the universe itself. Perhaps the universe is organized like a fractal, with similar patterns repeating at every scale, each level containing as much complexity and richness as every other level. If this is true, then our planet-sized atoms might not be imaginary constructs, but real phenomena occurring at scales we haven't yet learned to observe. Just as bacteria were invisible to us before we invented, microscopes and galaxies were unknown before we had telescopes, planet-sized atoms might be all around us, invisible not because they're too small or too far away, but because they exist at a scale we haven't learned to perceive. Let me share with you a thought that has haunted physicists and philosophers for generations. What if our entire universe, everything we can see and measure and know, is actually just an electron in an atom in some larger cosmos? The observable universe is finite in size, about 93 billion light-years in diameter. It's expanding from an initial hot, dense state. It has a specific set of properties and constants. Could these be the properties of a single particle in a larger reality? This idea might seem absurd at first, but consider the similarities. The universe is expanding, which could be analogous to an electron jumping to a higher orbital. The cosmic microwave background radiation could be the quantum glow of our electron universe in its current energy state. Dark energy, the mysterious force causing the expansion to accelerate, could be the quantum pressure preventing our electron universe from collapsing back to a lower orbital. The fundamental constants of nature, the speed of light, Planck's constant, the gravitational constant, could be the quantum numbers that define our electron universe's state. If our universe is an electron, then what we call the Big Bang might have been a quantum transition, our electron universe jumping from one orbital to another in some unimaginably vast atom. The entire history of our universe, 13.8 billion years of cosmic evolution, might be just a moment in the life of this cosmic atom, a brief quantum fluctuation that happens to contain all of space and time as we know it. But if our universe is an electron in a larger atom, then that atom must exist in an even larger universe, which might itself be an electron in an even larger atom and so on, infinitely upward. And in the other direction, the electrons in the atoms in our universe might themselves be universes, containing their own atoms with their own electron universes, its nested realities all the way up and all the way down, an infinite hierarchy of universes within universes within universes. This vision of nested realities isn't just philosophical speculation, it connects to real questions in physics. Why is gravity so much weaker than the other fundamental forces? Perhaps because it's leaking into other scales of reality, spreading across the nested hierarchies. Why is the universe fine-tuned for the existence of atoms and molecules and life? Perhaps because only universes with the right properties can exist as stable electrons in larger atoms, a kind of cosmic natural selection that ensures compatible physics at every scale. The idea of nested realities also offers a new perspective on consciousness. If every electron is a universe, and every universe is an electron, then perhaps consciousness too exists at every scale. The beings in electron universes might be conscious, thinking thoughts that to us occur in femtoseconds, but to them span eons. And we, in our universe electron, might be contributing to the consciousness of some vast being in the larger cosmos, our entire civilization just a fleeting thought in a mind too large for us to comprehend. But let's bring this back to our planet-sized atoms. If reality is truly nested, then planet-sized atoms might be the bridge between scales, large enough that we can imagine consciousness and complexity within them, but small enough that we can conceive of them within our universe. They might be the key to understanding how the hierarchy works, how information and causality flow between different scales of reality. Imagine that somewhere in our galaxy, there's a region where the nested structure of reality has become visible, where planet-sized atoms coexist with normal atoms, where the boundaries between scales have become permeable. In this region, you might see electrons the size of moons orbiting nuclei the size of asteroids, while normal atoms drift through the vast electron clouds like cosmic dust. You might witness chemical reactions happening on two different scales simultaneously, planet-sized molecules forming while normal molecules react within them. This multi-scale chemistry would create possibilities we can barely imagine. A planet-sized protein molecule might contain billions of normal molecules within its structure, each performing their own chemical functions while contributing to the larger molecule's behavior. It would be like a living city where the buildings themselves are alive, where every brick has its own metabolism while participating in the metabolism of the whole. Life in such a region would have to adapt to multiple scales simultaneously. Organisms might have planet-sized atoms as part of their structure, using them as cosmic organelles that perform functions impossible for normal atoms. They might use the slow, stable reactions of planet-sized molecules for long-term memory storage while using normal molecules for rapid information processing. They might exist partially in normal space and partially in the quantum realm of planet-sized atoms, bridging two different kinds of reality. These multi-scale organisms might perceive reality in ways we can't imagine. They might see the nested structure directly, observing universes within electrons and electrons within universes. They might communicate across scales, sending messages from our level of reality to the electron universes within their atoms, or to the cosmic beings for whom they are just electrons. They might be the universe's way of understanding itself, conscious observers who can perceive the full hierarchy of existence. The technology of such beings would be equally remarkable. They might build machines that operate across multiple scales, with planet-sized components controlling normal-sized components, controlling subatomic components. They might have computers that use the entire hierarchy for computation, storing data in electron universes, processing it at our scale, and outputting results to the larger cosmos. They might travel not just through space but through scale, journeying into electron universes or expanding into the larger reality of which our universe is just a part. But perhaps we don't need to imagine such exotic beings. Perhaps we ourselves are already multi-scale entities without realizing it. Our consciousness emerges from the behavior of neurons, which emerges from the behavior of molecules, which emerges from the behavior of atoms. We already span multiple scales of organization. Perhaps consciousness itself is the experience of being a bridge between scales, a pattern that exists across multiple levels of the hierarchy simultaneously. Think about what this means for free will and determinism. At the atomic scale, quantum mechanics introduces fundamental randomness. At the human scale, we experience the ability to make choices. At the cosmic scale, the universe evolves according to physical laws. Perhaps free will is what happens when patterns at one scale influence patterns at another scale, when the nested hierarchies interact in complex ways that can't be reduced to simple cause and effect. This nested view of reality also changes how we think about death and continuity. If every electron in our bodies is a universe, then we contain billions of universes, each with its own history, its own civilizations, its own stories. When we die, what happens to these universes? Do they die with us, or do they continue, dispersed into new configurations? And if our universe is an electron in some larger being, what happens to us when that being dies? Perhaps death and birth are just transitions between scales. When an electron jumps to a different atom, its universe doesn't cease to exist. It just finds itself in a new environment, part of a new molecule, contributing to new processes. Similarly, when we die, the pattern that is us might not disappear but might be incorporated into larger patterns, our consciousness merging with something greater, while the universes within us continue their own existence. The nested structure might also explain some of the mysteries of quantum mechanics. Why does observation cause wave functions to collapse? Perhaps because observation is an interaction between scales. When we observe an electron, we're a universe-sized pattern interacting with an electron universe, and this cross-scale interaction breaks the quantum superposition, forcing the electron universe to choose a specific state. Entanglement too might be understood through nested hierarchies. When two particles are entangled, perhaps their universes are connected through the larger scale, like two electrons in the same atom sharing orbitals. The spooky action at a distance that Einstein found so troubling might not be spooky at all, but simply the natural behavior of patterns that exist across multiple scales simultaneously. Dark matter and dark energy, those cosmic mysteries that make up 95% of the universe, might also be explained through nested hierarchies. Perhaps dark matter is the gravitational effect of structures at other scales, the massive electron universes or the containing atom, of which our universe is part, bleeding through into our reality. Dark energy might be the quantum pressure from the larger scale, the force that keeps our universe electron in its current orbital rather than letting it collapse. As we contemplate these nested hierarchies, we might wonder whether there's a larger scale and a smaller scale, or whether the nesting continues infinitely in both directions. Some theories in physics suggest there might be a smallest possible scale, the Planck length, below which space and time themselves break down. Similarly, there might be a largest possible scale, perhaps the size of the entire multiverse if it's finite. But perhaps these limits are just the boundaries of what we can observe from our position in the hierarchy. Just as an ant can't conceive of the size of the Earth, and the Earth can't conceive of the size of the observable universe, perhaps we can't conceive of scales beyond certain limits, not because they don't exist, but because they're too far from our position in the nested structure. If the nesting is truly infinite, then every point in space contains infinite complexity. The electron in a hydrogen atom in a drop of water in your body contains an entire universe, which contains atoms with electrons that contain universes, and so on forever. You're not just made of atoms. You're made of infinities within infinities, each as complex and rich as the universe you observe around you. This infinite nesting might seem to make everything meaningless. If there are infinite scales above and below us, what makes our scale special? But perhaps it's the opposite. Perhaps every scale is special, every level of the hierarchy equally important. The drama of human life, the evolution of consciousness, the quest to understand the universe, these might be playing out at every scale simultaneously, each version equally real, equally meaningful. Our planet-sized atoms in this view are not anomalies but necessities. They must exist somewhere in the hierarchy, bridging the gap between the atomic and the cosmic. They might be rare at our scale, but at other scales they might be common. In universes that are electrons in planet-sized atoms, normal atoms might seem impossibly small, while planet-sized atoms are the natural building blocks of matter. The search for planet-sized atoms, whether literal or conceptual, becomes a search for our place in the cosmic hierarchy. By imagining atoms larger than planets, we're really asking, where do we fit in the grand structure of existence? Are we at a special scale, or just one level, among infinite levels? Are the laws of physics the same at every scale, or does each scale have its own physics, its own chemistry, its own biology? These questions might seem purely philosophical, but they have practical implications. If reality is nested, if there are multiple scales of existence, then our future might involve not just exploring outward into space, but inward into scale. We might discover ways to communicate with the universes within our electrons or with the beings for whom we are electrons. We might learn to travel between scales, to exist simultaneously at multiple levels of reality. The technology to explore nested realities might start with our thought experiments about planet-sized atoms. By understanding how atoms would behave if they were planetary in scale, we might discover principles that apply across all scales. We might find universal laws that govern the nesting, rules that tell us how information and causality flow between levels, how consciousness emerges from and contributes to the hierarchy. As we develop quantum computers and other technologies that bridge the classical and quantum realms, we might be taking our first steps toward multi-scale technology. A quantum computer that maintains coherence across millions of qubits might be creating a kind of planet-sized atom, a macroscopic quantum system that exists at multiple scales simultaneously. As these technologies advance, we might find ourselves able to perceive and interact with other levels of the hierarchy. The implications for philosophy and spirituality are equally profound. Many spiritual traditions have long taught that reality is layered, that there are multiple planes of existence, that the material world is just one aspect of a larger reality. The nested hierarchy of planet-sized atoms and universe electrons might be a scientific glimpse of these ancient insights, a mathematical framework for understanding what mystics have experienced through intuition and meditation. And now, as we approach the end of our long journey through the cosmos of imagination, let us return to where we began, to that simple, impossible question that has guided us through realms of thought both scientific and fantastical. What if atoms could be bigger than planets? We've travelled far from that first whisper in the dark, explored territories of physics and philosophy that stretch the boundaries of what we thought possible, and yet the question remains as mysterious, as wonderful, as peacefully intriguing as when we first asked it. You've been patient with me through these hours of exploration, following as we've climbed from the quantum realm to the cosmic, as we've imagined electron clouds the size of solar systems and nuclei as dense as collapsed stars. Together, we've built a universe in our minds where the smallest things have become the largest, where the fundamental building blocks of matter have swelled to become the stages upon which cosmic dramas might unfold. And now, in these final moments before sleep perhaps claims you, let's reflect on what this journey has shown us, not about planet-sized atoms themselves, but about the nature of wonder, the structure of reality, and our place in the infinite mystery of existence. The truth is, we don't know if atoms could ever be bigger than planets. Our current understanding of physics suggests they couldn't, that the fundamental forces and constants of nature conspire to keep atoms tiny and planets huge, each in their proper place in the hierarchy of scale. But we've also seen that our understanding is incomplete, that there are mysteries in the universe that our theories can't yet explain, phenomena that hint at deeper levels of reality we haven't yet discovered, dark matter and dark energy, quantum gravity and consciousness, the fine-tuning of the universe and the arrow of time. These puzzles remind us that what we know is dwarfed by what we don't know, and perhaps that's the real gift of our impossible question. Not that it might have an answer, but that it gives us permission to wonder, to imagine, to explore possibilities beyond the boundaries of current knowledge. In imagining planet-sized atoms, we're really imagining a universe where our assumptions can be overturned, where the impossible becomes possible, where wonder never ends because there's always another scale to explore, another perspective to consider, another way of seeing the cosmic dance. Think back to all we've discovered on this journey. We've learned about Rydberg atoms, those real giants of the atomic world that prove atoms can be far larger than we usually imagine. We've explored neutron stars and white dwarfs, cosmic objects where quantum mechanics operates on astronomical scales. We've contemplated the possibility that our entire universe might be an electron in some unimaginably vast atom, and that every electron in our world might contain its own universe. We've imagined what it would be like to live inside a planet-sized atom, to experience quantum superposition directly, to exist as a probability cloud rather than a definite object. Each of these ideas, whether grounded in established science or floating in the realm of speculation, has shown us something important, that reality is far stranger, far more beautiful, far more mysterious than our everyday experience suggests. The solid world around us, the world of chairs and tables and sleeping bodies, is actually made of empty space and probability clouds. The stars above us, those points of light that have guided humanity since our beginning, are actually fusion reactors converting matter into energy according to Einstein's famous equation. The universe itself, all of space and time and everything within it, emerged from a point smaller than an atom and might one day return to such a point, or expand forever into cold emptiness, or undergo some transformation we can't yet imagine. In this context, the question of planet-sized atoms becomes less about whether such things could exist, and more about what their contemplation teaches us. They teach us humility, reminding us that our intuitions about size and scale are limited by our evolutionary history, shaped by the needs of survival on one small planet, rather than by the fundamental nature of reality. They teach us creativity, showing us that by combining concepts that seem incompatible, the microscopic and the astronomical, we can discover new ways of thinking about both. They teach us connection, revealing the deep links between the quantum and the cosmic, the way patterns repeat across scales, the unity underlying the apparent diversity of phenomena. As you lie there in the darkness, perhaps on the edge of sleep, consider how remarkable it is that you can even contemplate planet-sized atoms. Your brain, a collection of atoms arranged in specific patterns, can imagine atoms billions of times larger than those that compose it. The atoms in your neurons, following the laws of quantum mechanics and thermodynamics, can conceive of different laws, different sizes, different universes entirely. Your matter contemplating matter, atoms thinking about atoms, the universe becoming conscious of itself and wondering what else it might be. This capacity for wonder, for imagination beyond the boundaries of immediate experience, might be the most precious thing about consciousness. Other animals can solve problems, use tools, even show creativity, but as far as we know, only humans can ask, what if, about things that have no practical relevance, no survival value, no purpose except the pure joy of wondering. When we imagine planet-sized atoms, we're exercising this uniquely human gift, this ability to transcend our physical limitations through thought. And perhaps that transcendence is more than just imagination. Perhaps when we conceive of planet-sized atoms, we're in some sense creating them, bringing them into existence in the realm of thought, if not in physical reality. After all, mathematics, the language we use to describe these impossible atoms, seems to exist independently of physical reality. The equations that govern planet-sized atoms are just as valid, just as beautiful, just as true as the equations that govern real atoms. In the Platonic realm of mathematical truth, planet-sized atoms are as real as anything else. Some physicists and philosophers go even further, suggesting that physical reality itself might be mathematical, that what we call matter and energy are just particularly stable solutions to cosmic equations. In this view, planet-sized atoms might exist not as physical objects, but as mathematical structures, patterns in the cosmic computation that is reality. They might be calculating themselves into existence right now, in some corner of mathematical space we haven't yet learned to access. But let's return from these abstract heights to the gentle question that brought us here. What if atoms could be bigger than planets? After all we've explored, the question feels different now, doesn't it? It's no longer just a wild impossibility but a doorway into deeper questions. What determines the size of things? What is the relationship between the quantum and the classical? How does complexity emerge from simplicity? Is there a largest possible atom or a smallest possible planet? Could the constants of nature be different? Are they different elsewhere in the universe or in other universes? These questions don't have answers, or at least not answers we know yet. But that's what makes them perfect for contemplation as sleep approaches. They're questions that invite exploration rather than demanding resolution, that open minds rather than closing them, that create peaceful wonder rather than anxious uncertainty. They're questions that remind us that the universe is not a problem to be solved, but a mystery to be experienced, not a test to be passed, but a gift to be received. As our journey together draws to a close, I want to leave you with a thought that might accompany you into sleep and perhaps into dreams. Every atom in your body, every one of those tiny probability clouds that together create the miracle of you, was forged in the heart of a star that died billions of years ago. You're made of cosmic stuff, assembled from the ashes of ancient suns, organized into patterns complex enough to wonder about their own origins. In a very real sense, you are the universe looking at itself, asking itself questions, imagining itself differently. And if you are the universe contemplating itself, then your imagination of planet-sized atoms is the universe imagining itself at different scales, exploring its own possibilities, wondering what else it might be or might have been. Your thoughts about these impossible atoms are as much a part of the cosmic story as the actual atoms themselves. In the grand narrative of existence, from Big Bang to whatever comes after, this moment of wondering about planet-sized atoms is a verse in the cosmic poem, a note in the universal symphony. Perhaps tomorrow you'll wake and forget about planet-sized atoms, return to the world of normal-sized things and practical concerns. But something will remain, some residue of wonder, some expansion of possibility. You'll know, even if you don't consciously remember, that you've travelled to places where atoms can be worlds and worlds can be atoms, where the impossible becomes possible through the simple act of imagination. You'll carry with you the peaceful knowledge that reality is far stranger and more beautiful than it appears, that mysteries exist at every scale, that wonder never has to end. The night continues around you, filled with its own mysteries. Perhaps outside your window stars are shining, each one a fusion reactor converting hydrogen into helium, creating the elements that will one day become new planets, new life, new consciousness. Perhaps clouds are drifting across the moon, water molecules that have been cycling through Earth's atmosphere for billions of years, each molecule made of atoms that have their own long histories. Perhaps somewhere in the darkness, in a laboratory or an observatory, scientists are discovering something new about atoms or planets, adding another piece to our ever-growing understanding of the cosmos. Or perhaps the night is quiet, peaceful, inviting you to rest. Perhaps your breathing has already begun to slow, your muscles to relax, your thoughts to drift toward dreams. If so, let them drift. Let them carry you to places where atoms can be as large as worlds, where you can walk through electron clouds and dance with probability waves. Let them show you universes within electrons and electrons within universes, infinite hierarchies of existence, all equally real, all equally wonderful. And remember, as you drift towards sleep, or perhaps are already there, that the question we've explored tonight, what if atoms could be bigger than planets, is really just one variation of the eternal question that drives all science, all philosophy, all human curiosity. What if things were different? What else is possible? What wonders await discovery? These questions have no final answers because every answer opens new questions, every discovery reveals new mysteries, every level of understanding points to deeper levels yet to be explored. This is the gift of consciousness, the burden and the joy of being human, to ask questions that have no answers, to imagine impossibilities, to wonder without end. And in that wondering, in that peaceful contemplation of cosmic possibilities, we find not answers but something better, connection to the infinite mystery of existence, participation in the cosmic dance of matter and energy, information and entropy, being and becoming. So as you rest now, whether in sleep or in peaceful wakefulness, know that you've been part of something beautiful tonight. You've joined the ancient human tradition of wondering about the nature of reality, of imagining the universe differently, of finding peace in contemplation of the infinite. You've travelled from the smallest scales to the largest, from the quantum to the cosmic, from the possible to the impossible and back again. You've seen that atoms and planets, despite their vast difference in size, are part of the same cosmic story, different verses of the same universal poem. The question that brought us together, what if atoms could be bigger than planets, remains unanswered in any definitive sense, but that's as it should be. Some questions are too beautiful to answer, too rich to reduce to simple yes or no, too important to close off with certainty. They're questions that keep us wondering, keep us exploring, keep us connected to the mystery that surrounds and includes us. And so, as this journey ends, the greater journey continues. Tomorrow you'll wake into a world made of atoms, living on a planet, under stars that are fusing atoms into new elements, in a universe that might itself be an atom in some larger reality. You'll carry with you, perhaps unconsciously, the wonder of planet-sized atoms, the peace of cosmic contemplation, the knowledge that reality is far stranger and more beautiful than it appears. The atoms in your body will continue their quantum dance, electrons in probability clouds around nuclei, forming molecules that form cells that form you. The planet beneath you will continue its orbit around the sun, held by gravity in a cosmic dance that's been going on for billions of years. The universe will continue its expansion, carrying galaxies apart, creating new space between the stars, perhaps preparing for transformations we can't yet imagine. And somewhere in all of this, in the dance of atoms and planets, in the expansion of space and the flow of time, in the emergence of consciousness and the asking of impossible questions, there is peace. Not the peace of having all the answers, but the peace of being part of the question. Not the peace of understanding everything, but the peace of wondering about everything. Not the peace of certainty, but the peace of mystery. This is what I wanted to share with you tonight. Through all these hours of exploration, through all these words about planet-sized atoms and quantum probability and nested realities, not facts to be memorized or theories to be believed, but wonder to be experienced, peace to be felt, mystery to be embraced. The universe is vast and strange and beautiful, and you are part of it, made of it, inseparable from it. Every atom in your body connects you to the cosmos. Every thought in your mind adds to the universe's self-awareness. Every moment of wonder increases the total wonder in existence. What if atoms could be bigger than planets? We still don't know. But in asking the question, in following it wherever it leads, in allowing ourselves to imagine the impossible, we've discovered something perhaps more valuable than any answer. We've discovered that wonder has no limits, that imagination has no boundaries, that the universe is generous with its mysteries, always offering more to explore, more to contemplate, more to peacefully wonder about. And now, as words fade into silence and thought dissolves into dream, let the question rest gently in your mind, not demanding an answer, but offering an invitation to wonder, to imagine, to explore. An invitation to see the universe not as a collection of facts to be known, but as an infinite mystery to be experienced. An invitation to find peace not in certainty, but in curiosity, not in answers, but in questions, not in knowing, but in wondering. What if atoms could be bigger than planets? What if they already are, somewhere, somewhen, in some dimension of possibility we haven't yet discovered? What if the question itself is the answer, the wondering itself the destination, the journey itself the home we've been seeking? What if? What if? What if? Let these gentle wanderings carry you now, into sleep perhaps, into dreams certainly, into the vast and peaceful mystery of existence where atoms and planets, the quantum and the cosmic, the possible and the impossible, all dance together in the eternal ballet of being. The universe continues its patient spinning, atoms vibrating in their quantum clouds, planets orbiting their ancient stars, galaxies drifting through the cosmic dark, and you, made of atoms, living on a planet wondering about it all, are the universe knowing itself, questioning itself, imagining itself anew. In your peaceful wondering about planet-sized atoms, the cosmos whispers its deepest secret, that the mystery is the meaning, the question is the answer, and the wonder, the eternal wonder, is the point of it all. Sleep well, fellow wanderer. Dream of atoms the size of worlds and worlds the size of atoms. Dream of electrons that contain universes and universes that are electrons. Dream of the infinite nested hierarchies of existence, each scale as real and rich as every other. Dream of yourself, made of star stuff, contemplating stars, a temporary arrangement of atoms that can conceive of atoms being arranged differently. Dream of the beautiful impossibility of it all, the magnificent mystery of existence, the peaceful wonder that never ends. And when you wake, whether in minutes or hours, whether to sunlight or continued darkness, remember this. You've travelled to the edges of possibility and back. You've imagined the unimaginable. You've wondered about wonders. You've been, for these few hours, a conscious part of the universe's contemplation of itself. And that, more than any answer to any question, is the gift, the miracle, the reason for it all. What if atoms could be bigger than planets? We may never know. But in the asking, in the wondering, in the peaceful contemplation of cosmic possibilities, we've found something precious. Our place in the infinite mystery, our role in the cosmic story, our connection to everything that is, was, and ever could be. And that, dear friend, is enough to carry us peacefully into sleep, into dreams, into whatever wonders await us in the darkness and beyond. The question remains, floating in the space between waking and sleeping, between the known and the unknown, between the possible and the impossible. What if atoms could be bigger than planets? Let it float there, unanswered but beautiful, impossible but inspiring, a gentle reminder that the universe is far stranger and more wonderful than we can imagine, and that we, made of atoms living on a planet, are part of that strangeness, part of that wonder, part of the eternal question that is existence itself,